Chemistry, madam is fine.
Arjun, shall I start?
1 second, sir. I will clarify. Sarita, madam, are you ready?
ఆయన చదివానిలే లేట్ అవుతుంది కదా.
Okay.
Okay, good afternoon all of you.
Unmute చేసుకోండి సరిత మేడం, ఒకసారి అన్మ్యూట్ చేసుకోం.
Unmute చేశాను sir.
Very good. Start up, ma. Very good. Okay. Very good.
A very good afternoon to invited guest speakers, Honorable Vice Chancellor of Palamuru University, Dr. Rahul Bojja garu, Registrar Palamuru University, Professor Pindi Pavan Kumar garu, OSD2 Vice Chancellor Dr. Madhusudan Reddy garu, Examination Dr. Nagam Kumaraswamy garu, respected Principal Dr. Prabhaker Reddy garu, and all the registered participants on the behalf of University College of Pharmaceutical Sciences, Palamuru University. I feel privileged to extend my heartily welcome to you all to the International Webinar Series Day 6, organized by Palamuru University, collaborated with Indian Pharmaceutical Association. We are honored to inform to you that today's session is 13, and the topic is Introduction to 2D NMR Techniques. And the speaker of the session is Professor Girija Mangatayar. It's my immense pleasure to introduce the speaker of the session, a well-known personality, Professor Girija Mangatayar garu. Heartily welcome, madam.
Thank you.
Madam is presently working as a professor in Palamuru University in the Department of Chemistry. Madam was a former registrar, controller of examination, and joint director for the academic cell, and vice chancellor nominee, and also governing body member. Madam has a splendid experience of 27 years in the teaching and 16 years in the research. Madam has around 25 national international publications while also holding a patent. She also holds a professional membership in American Chemical Society and Association of Chemistry Teachers and Indian Council of Chemists. And Madam also is an editorial board member of International Journal of Environmental Chemistry and International Journal of Chem Informatic Research and Journal of Biomolecular Research and Therapeutics, International Journal of Nanoscience and Nanotechnology. Thank you, madam, for accepting our invitation and conducting this session. Over to Prabhaker Reddy, sir.
Ma'am, thank you, madam. Thank you, Sarita, for your valuable information about Professor Girija Madam garu. I welcome Girija Madam to start the session.
Okay. Yeah.
Ma'am, please.
Okay. I'll just. So good afternoon. I welcome all the participants, and first of all, let me congratulate the organizers, especially the Pharmaceutical College of Palamuru University, the chairman of this particular webinar, Dr. Prabhaker Reddy, and the conveners of different sessions. And in fact, the webinar, which has been organized by this particular department in collaboration with Pharmaceutical Society, is in fact, it is very much need of the hour in the present pandemic situation. So where all the participants are getting an opportunity to interact with a galaxy of speakers all over the world. And all the lectures that are delivered so far are not only relevant to the pharma students, but also very much relevant in this present situation to every one of us, because we have been facing this particular situation for about 3.5 months or so, and coming to know about the information relating to the COVID-19 from the TVs and from the newspapers and from the WhatsApp messages, but still we feel that we need to know a lot about this as pharmacists. And I feel that the speakers who have delivered the lectures so far, they have covered almost most of the relevant topics, like the impact of COVID on pharmaceutical marketing, research and development in COVID scenario using CAD, that is computer aided drug design, and emerging therapeutic interventions for COVID-19. And finally, it is once again emphasized or proved that there is no dearth for job opportunities for the pharmacy students, even in this critical situation, that is pandemic situation. And in fact, the world now needs the contribution of the pharmacists or the pharma industry more than anyone else. So in that way, I think all the participants had a very great interaction and hope that they have greatly benefited with these lectures. And the webinar has provided them a great platform to share all the views and to know about all the day-to-day developments in this pharma industry. And finally, coming to my topic, I am more confined to the classroom because the topic which I am going to cover is more relevant for the students because it is a part of the syllabus. And the techniques, this is nothing but the techniques, 2D NMR techniques, which are useful to any research students, wherein the molecules of whatever compounds or the new molecules they're going to discover or develop, they first of all, they have to find out what are the structures of these molecules. And finally, they have to come to a conclusion regarding the structures of the molecules. And the topic which I'm going to deal is covering that part of it. So I'll introduce my topic, that is 2D NMR techniques. And this is relevant to the NMR. And I think all the participants, definitely they'll have to be really very attentive in this because it is something which is related to the part of the syllabus. So the NMR, as you all know, so I'm going to talk about the advanced NMR, that is 2D NMR techniques, how they are useful for the structural
Madam,
elucidation.
one second, madam.
Yes.
Video is off, madam.
Video is
Yes,
off.
ma'am. Yes, sir.
Till now, even now? Yeah, I'm sorry.
No. Screen was on, ma'am. Your video is not on, ma'am.
Okay.
Yes, ma'am. Perfect.
Okay. Yeah.
Thank you.
Okay. Now, both even I'm visible now.
Sharing slide, ma'am.
Yeah.
Yes.
Yeah.
Yes, ma'am. Now
Okay.
it's perfect.
Yeah. So I'm going to deal about the 2D NMR techniques, the advanced 2D NMR techniques, how they are useful to find out the structures of the molecules. So as I'm saying, my topic today is 2D NMR, then definitely you will have in your mind, if we are talking about 2D NMR, there must be something else about something which is nothing but 1D NMR. So 1D NMR, so before I go into the details of 2D NMR, I'll just briefly differentiate between what is 1D NMR and what is 2D NMR. And I think all the participants, they know about the NMR technique and the NMR experiments. And the 1D NMR is nothing but we have different kinds of NMR. It's a nuclear phenomena. So whatever nucleus we are trying to study, that should be magnetic and it should be active and it should give an NMR spectrum. So likewise, in order to find out the structures of organic molecules, because they are nothing but the hydrocarbons, they have both carbon and hydrogen. So we have to know about the hydrogen is nothing but proton and carbon spectrum. So all the NMR what we have discussed so far, that is proton and C13, nitrogen 14, phosphorus 31, fluorine 19, and so on, they're all basically 1D NMR. 1D NMR is nothing but we are making use of only one dimension. One dimension means only one axis to find out the structures. And one axis, the axis is the conventional axis, is nothing but the x-axis. So that is what is 1D NMR. And 2D NMR is we are going to make use of two axes to represent the information. So now we'll actually in my lecture, you'll come to know the need for 2D NMR and what exactly you're going to see in the 2D NMR. So 1D NMR is nothing but it is used to solve the structures of simple to moderately complex structures of molecules, which is a plot of frequency versus intensity. So in the slide, I'm showing the spectrum on to the right. You just don't bother about the pulse sequence. I'll talk about that later on. So I have shown the PMR spectrum. PMR is nothing but proton NMR spectrum of ethanol. Ethanol is CH3, CH2, OH, that is ethyl alcohol, wherein the NMR spectrum, the proton NMR spectrum is showing 3 peaks. So the downmost signal around 3.8 is due to CH2, and then OH, and then CH3. So if you just look into the structure, the spectrum, you find 3 signals. The 3 signals means the number of signals is according to the number of non-equivalent nuclei. And here the spectrum we are talking about is PMR. So the nucleus is nothing but proton. So you get 3 different signals because there are 3 different kinds of protons, isn't it? In ethyl alcohol, CH3 is one kind of a signal, one kind of a proton, CH2 is another kind, and OH is another kind. So hence we find 3 signals. And the multiplicity, each signal is split according to the n+1 rule, where n here signifies the number of protons on the neighboring carbon. So accordingly, CH2 is split into a quartet, and OH singlet, and CH3 a triplet. But here the spectrum is not exactly a quartet for CH2, singlet for OH, and a triplet for CH3. Yeah, CH3 is triplet, but CH2 and OH, they are slightly different. This is because of pure ethyl alcohol spectrum, where CH2 is further split and OH couples with CH2. So you're going to find a triplet for that. So if you combine the information, and the integration here shows about CH2 is for 2 protons, OH is for 1 proton, and CH3 is for 3 protons. So if you compile all the information, or if you combine all the information and put it on a paper and try to write down, get the information regarding the structure of the molecule, you'll come to know that it is ethyl alcohol spectrum. So that is how we are going to analyze the spectrum and know the structures of the molecules. And then if so, then this is slideshow or whatever. Okay. Slide. If this is the case, then why is there a need for a 2D NMR spectrum? So this is this holds good for simple molecules like ethyl alcohol, or where the number of protons are very less, and the chemical shift values are the chemical shift values are not close by. That means the signals are very far apart. I have shown this spectrum. But for complex molecules, where the number of protons, non-equivalent protons, are more, yeah. So this in this slide, so where if suppose you're talking about a complex molecule like progesterone, which is shown in this slide, that is 6-methyl progesterone, where you have 24 different kinds of protons. The structure of the molecule is also given, where there are 24 different kinds of protons. And this, if you look at the spectrum below, the spectrum is too complicated. You have different signals, and all the signals are in fact they're overlapping. Unlike in the previous slide, where the signals are very far apart, but here the signals are getting overlapped. So this is because there are 2 reasons for the signals to get overlapped. One reason is the more number of protons, and the chemical shift values are also very close by. So when the number of signals are more, and if the chemical shifts are very close by, automatically there is every chance that the signals get overlapped. So is there any solution for this? Definitely there is a solution for this. So the solution is what? Since the signals are getting overlapped, in order to find out what exactly is the structure, we'll have to resolve the signals. And the solution for resolving such a situation is, one is using shift reagents, and the other is using high resolution techniques. That means when you are going to record the spectrum, instead of a 200 megahertz or 60 megahertz or 80 megahertz or 90 megahertz, you have to record the spectrum on a high resolution spectrophotometer like 400 megahertz or 600 megahertz. And in fact, the spectrum which is shown here is run on 1400 megahertz, 400 megahertz instrument, but still the resolution is less. Is not the resolution is not to the extent to be actually needed. So in such cases, this is of little help, isn't it, for complex molecules? And in such cases, we need more advanced techniques, and that is where we come across the 2D NMR technique. So So 2D NMR technique, it is introduced by Jean Jenner in 1971, wherein it is used for the separation of signals when shift reagents and high resolution techniques have little effect. So what exactly is being done in these particular experiments or in these techniques? An additional time interval is inserted between the preparation and the detection. So if you just look back into the first slide, yeah, now we'll come back to the pulse sequence. I said I'm going to explain about this later. So now the situation has arisen. Now we talk about this. In 1D NMR experiment, there are only two time phases. One is preparation and the other is detection. That means when, in order to excite the nucleus, we have to give a pulse, and the pulse covers the frequencies over a wider range. So that is nothing but a preparation. Normally during the preparation period, a 90-degree pulse is given, and immediately after the pulse is given, the signal is being detected, because this particular signal is with respect to time, it decays with time, so that is converted into a frequency domain signal using a mathematical program called Fourier transformation. So immediately after the signal immediately after the pulse is given, the signal is detected. That is the 1D NMR. So the information pertaining to the structure of molecule with respect to the delta values and J values. So in the proton NMR, in any NMR spectrum, there are two parameters by which you can know the structures. One is chemical shift values, that is with respect to the position of the signals, and the other one is J value, that is coupling constant. So both are measured on the x-axis in the 1D NMR. So whereas in 2D NMR, what is happening here is we are introducing one more additional time period. That is what is called evolution. So sometimes even we may have 3 periods. That means between preparation and detection, there is an additional time interval, which is nothing but evolution. And sometimes it is all divided into another time period called mixing time, depending upon the type of 2D NMR experiment. Because we have various types of 2D NMR techniques, and each technique gives a different kind of information. So additional time period is inserted between preparation and detection. And in this period, what is happening is the NMR receiver is not active. It is inactive. So that the signal is not detected immediately, unlike in the case of 1D NMR. So what is happening in this period? The nuclear spins or the nuclear magnets. We call all the protons or any nucleus, whether it is C13 NMR or proton NMR or fluorine NMR, fluorine 19 or phosphorus 31 NMR, whatever NMR we are referring to, that we are calling that as nucleus. And that nucleus in the NMR language, we call them as spins, because they have a spin, they'll interact in the magnetic field. Because in the NMR, we are not only subjecting the sample to irradiation with radio frequency signal, but also we are giving additional frequency field, that is nothing but a magnetic field. So the nuclear spins, they interact and they come out with the new information. So they're coming out with evolution. So that is what, hence this period is called as evolution. So the signal is not detected immediately. So we have now, since we have two time intervals, T1 and T2, unlike in the case of 1D NMR, we'll have to do Fourier transformation twice. Whereas in 1D NMR, we are doing Fourier transformation only once. So now we'll see the basic differences between 1D and 2D NMR. So with respect to 1D NMR, the induced magnetization varies with only one time variable, because immediately after the pulse is given, we are detecting. That we are calling as that time period, we are calling it as detection, or it is also called as T2. And in 2D NMR, it varies with two time variables. One is T1 and other is T2. So T2 is the original one, and T1 is a new one. That is what is evolution. So now, naturally, as I said before, in 1D NMR, since there is only one time variable, we are going to do the Fourier transformation only once. That is with respect to T2. Whereas here in 2D NMR, we are going to do Fourier transformation twice, one with respect to T1 and the other with respect to T2. And always T2 is the prime, T2 is of prime importance. So that the Fourier transformation with respect to T2 is coming first. So that will occupy only the x-axis. And what are the different axes? How many axes we are going to use in 1D NMR? In 1D NMR, we are going to use two axes. One is x-axis and y-axis. But the information pertaining to the NMR is reflected, displayed only on the conventional traditional axis, that is X. That is NMR, the main information what you're going to extract from NMR is nothing but delta and J. Delta is chemical shift and J is coupling constant. And that is coming only on the X axis, and the Y axis is intensity. That is with respect to the number of protons, if it is a proton NMR. That is with respect to intensity, and which is not of much use. So naturally, the main importance is only with respect to one axis, that is X axis. Both the information are seen, that is delta and J. Whereas in 2D NMR, we make use of three axes. One is X, Y, and Z. X is delta, and that is chemical shift. Y is either chemical shift or coupling constant. Depending upon the type of 2D NMR, we may have either coupling constant information, that is J, or again the same chemical shift information. And again, the third axis Z axis is with respect to intensity. And the number of phases or the time periods in 1D NMR, as I said, only two, that is preparation and detection. Whereas in 2D NMR, we have mainly three periods. We call it as preparation, detection. In between these two, we have evolution. Sometimes it is four. So normally we are not bothered much about here. So we call normally as three periods. And how is the signal and how is the signal represented in 1D NMR? In 1D NMR, the signal is always represented in the form of peaks, as we have seen before with respect to ethyl alcohol proton NMR spectrum. We have seen all the signals, isn't it? Whereas in 2D NMR, the information is reflected in the form of either contour spots or stacked plots. See, now the basic differences between 1D NMR and 2D NMR. The spectrum. See, onto the left, we are seeing the proton NMR spectrum of ethyl alcohol, and onto the right, we are seeing the proton, the same proton NMR, 2D NMR spectrum we are just seeing. So here the same ethyl alcohol molecule we are seeing. So onto the left, 1D NMR, methylene, then OH, then CH3. So similarly, 2D NMR, here this is not, every 2D NMR doesn't look so. This is a kind of a 2D NMR. There are, as I said, there are different kinds of 2D NMR. This is one of such 2D NMR spectra, and this is a rosy spectrum where the signal, the quartet CH2, as I said, it is a quartet. So here the quartet is representing in the form of four different spots. And the OH singlet, so it is seen only one single spot, and CH3 triplet, so three spots are seen. So this is nothing but the 2D NMR representative. Basically, it is that. And now if you go into the details of the experiment, 2D NMR experiment, so preparation, what exactly is done in preparation? In preparation, the nuclear magnets are allowed to relax to their equilibrium state. We are preparing the nucleus. We are preparing the nuclei to their equilibrium state, so that the excess nuclei are always maintained at the ground level, so that we get a very well-defined peak. Okay, that is what is called a preparation. Since we are preparing the nuclei, more nuclei to be present in the ground level, so that we get an well intense peak. So this period is called as preparation period, which is of 10 seconds. And next, evolution period, where the evolution period T1, it changes. Okay, it changes from experiment to experiment, and it changes the phase and amplitude of the peaks acquired during T2. And mixing period is of a finite duration. Either it varies from 0 to finite stage. And finally, it is a detection period where we are going to finally we are going to see the signal. So the experimental procedure, if you look into it, as I said, the signals before doing the Fourier transformation, the signals, they decay with time. So they'll be in the form of sine wave, which decays with time, which we're calling it as free induction decay. And if suppose we look at this spectrum in this form FID, we just cannot interpret what exactly or what is information present in that FID. In order to understand, in order for us to understand and analyze, that signal has to be converted into a frequency domain signal. So the program which is used to convert this time domain signal, which is decaying with respect to time, which is in the form of a decaying sine wave, we are trying to convert that into a frequency domain signal, and the program is called Fourier transformation. So here, since we have two time periods, T1 and T2, first always, as I said, it is T2 which is done the Fourier transformation, because the information with respect to T2 is always seen on the conventional axis, that is nothing but the x-axis. And after that, it again, if the Fourier transformation is done in T1, so first over T2, that is over rows, and again over column. So finally, we get this spectrum like this. So double transform involving two intensity and two time variables are used. And see, this is how the final spectrum looks. On to the left, you can see the spectrum is represented in two different ways. One is stacked plots above, and the other one below here is contour peaks, contour spots. So the experiment, there are different experiments. It is not just one experiment. So in one experiment, we give a pulse and then we give some time and then detect. And again, in another experiment, we give a pulse and then we allow the nuclear magnets to interact and then we detect. So we are doing series of experiments, and the reason for doing so such series of experiments is in each experiment the information pertain to T1. See, in all the experiments, if you closely observe, the T2 is the last after the second 90-degree pulse is given, the detection, it remains the same. But the T1 is varying from experiment to experiment, and each experiment we are trying to slowly augment. We are slowly increasing the time. So we are collecting the information in each experiment. We are collecting, we are recording, collecting, and storing. And finally, we are adding up all the information which is obtained in different experiments. And finally, we are trying to amplify and trying to give the information at last. So the reason for carrying out so many experiments is some of the nuclei which are not abundant. For example, C30 nucleus, it is less abundant compared to proton. So it is called as a insensitive nucleus. And in such cases, the information which is obtained in different experiments, in each experiment, what we are doing is the signal is enhanced to certain extent. So we collect all this information, we add up, and then finally the spectrum is given. And that is what is the purpose. So this is what is the 2D technique. So in 2D technique, finally the information, because in 2D NMR is nothing but it is a 3D. We are calling it as a 3D picture, and the 3D picture we are trying to represent in the 2D, because we, in order to represent the picture, we are using either a blackboard or a paper. So the paper or blackboard both are two-dimensional. So whenever we are trying to represent a 3D picture, 3D pictures means what? All real objects. We are calling them as 3D pictures, like mountains, for example. So they are seen in the 3D, isn't it? And that we are trying to represent in the 2D form. So definitely there is no other way to represent the 3D picture in 2D form, either in the form of contour peaks or stack plots. That is the reason why we are going to, they are represented in the form of contour spots. So this, I think I have given enough introduction for the 2D NMR, and there is not much needed for you to understand the details of the experimental procedure. We only restrict ourselves to the applications, what are the different techniques of 2D NMR and how they are useful in knowing the structures of the molecules. So different techniques, there are different techniques. One is 2D J-resolved spectroscopy, which is called ROSI. ROSI is resolved spectroscopy. So what resolution we are doing? J resolution. So J is nothing but couplings. Okay. So next is correlation spectroscopy. Correlation spectroscopy is nothing but COSY. We'll talk about this in detail when we talk about the COSY. Next, total correlation spectroscopy, which is also called as TOCSY. And then heteronuclear multiple quantum coherence, HMQC, heteronuclear multiple bond coherence, HMBC, and then nuclear Overhauser effect spectroscopy, that is nothing but NOSI. And finally, it is inadequate, 2D inadequate, which is called incredible natural abundance double quantum transfer experiment. So we are going to talk about each of these techniques separately, and I'll try to maximum possible, I'll try to explain, take simple molecules, even though I said in the beginning, we are going to make use of these techniques only for the complex molecules in order to resolve the structures of complex molecules where the signals are getting overlapped. But to make you understand, we'll start with the simple molecules and we can apply later on. With this information, we can use this technique to elucidate the structures of complex molecules, especially natural products, alkaloids, terpenoids, steroids, where they have more number of different kinds of nuclei, and the spectrum is very complicated and we cannot analyze. So normally the spectrum is analyzed based on n+1 rule and signal height rule, and all those basic rules are followed. And that is possible only when the molecule is simple. Okay, when the molecule becomes more and more complicated as far as the number of different kinds of nuclei are concerned, the signals get overlap. And in such cases, we can make use of resolved spectroscopy or COSY or anywhere, anything else. So mostly we use only ROSY and COSY, and only in specific cases we use NOSY. And only in really very specific cases we use 2D inadequate. Okay, let us come to 2D J resolved spectroscopy. So 2D J resolved spectroscopy, in a simple form, in a nutshell, onto the left, um, onto the right side, you have the spectrum where the x-axis is representing the chemical shifts, and the y-axis is representing the couplings, the coupling constants, the coupling information. So as we are saying, the y-axis is representing the coupling information. And as we all know that the couplings are of two types, isn't it? The couplings are of two types. What are the different types of couplings? Couplings can be between the similar nuclei or between different nuclei. If the coupling is between similar kind of nuclei, that is, if the coupled nuclei are of the same kind, we call it as homo coupling. And the spectrum, 2D spectrum or the 2D NMR spectrum, which is pertaining to this information, is called as homo-ROSY. And if the coupled nuclei are of different kind, it is called hetero-ROSY. So basically, ROSY is delta on x-axis, J on the y-axis. And what is this J is based on the nature of coupling interaction. If it is homonuclear coupling interaction, we'll have to resort to homo-ROSY. And if it is heteronuclear couplings, what we want to observe, we'll have to go to hetero-ROSY. So before that, you all know what kind of coupling interaction we are going to find out in proton NMR. Let us understand this 2D NMR with respect to proton and C13 only. Let us restrict only to this, because we are talking about organic molecules, and organic molecules are basically hydrocarbons, where this main skeleton is carbon framework with the hydrogens on it. So definitely we have to have an idea as to what is proton NMR and what is C13 NMR. And in proton NMR, we basically observe only the coupling between proton and proton. So we are going to observe only homonuclear couplings. Whereas when it comes to C13 NMR, we come across heteronuclear couplings. So carbon coupling to proton. So homonuclear couplings we observe in proton, and heteronuclear couplings we observe in C13 NMR. So homo means, it is homo-ROSY means we are referring to proton NMR. Hetero-ROSY means we are referring to C13 NMR. Now I think you have understood that is 2D NMR is nothing but it is only the conventional NMR, but we are trying to represent the information in the form of a 3D picture, which you are trying to represent in the 2D form. Okay, two-dimensional, we are trying to show the 3D picture. So 2D is nothing but it is only the conventional NMR. Only thing is because of the overlapping of multiplets, because there is no proper resolution, we are resorting to 2D NMR. We are not getting any different information. Only that information we are getting in a more refined way, more resolved way. So you have to understand one thing. Homo-ROSY means proton. Hetero-ROSY means C13 NMR. So it separates the proton chemical shifts along the x-axis and proton-proton coupling constant values along the y-axis in the spectrum. So it is a powerful technique for resolving complex multiplex of 1D NMR. As I said, it is only a technique to resolve the complex multiplets, where if suppose the shift reagents are high resolution spectrophotometers are not doing much resolution, then we go to the 2D NMR technique. So where the pulse sequence, this is the normal pulse sequence. We are giving 90-degree pulse followed by 180 degrees, and then the detection is taking place. So in between is evolution period. So this is just a pulse sequence which is maintained, and you have a series of such experiments as I shown in my previous slides. This is how the basic pulse sequence looks. And here, see, and always in the 2D NMR, when you are referring to the 2D NMR, the box inside, see, the box inside is only the information pertaining to the 2D NMR. If you refer to X or Y axis, the X and Y axis, they do not give the 2D information. The information what we want to derive is only present inside the box. That is called the matrix. So only the matrix gives the 2D information. So on the X and Y, it is not the 2D information. X and Y, for reference, for our understanding, for our reference, we are giving the NMR spectrum. So on the top, there are two spectra which are reflected here. They are one and the same. It is a 2D picture. Inside it is 2D picture, and on the top we are showing the 1D NMR. In both the spectrum, there are two sections, above and below. So if you just refer to the above diagram, on the top of the box, we are seeing the 1D NMR. Okay, so now we are referring to 1D NMR. If you just look at the leftmost signal, there we are finding five signals, isn't it? 1, 2, 3, 4, 5 signals, and then we are seeing 4 signals, and then 3 signals, and then 2 signals, and the last one is single peak. So 5 signals onto the left indicates it's we are thinking that maybe if we don't look at the matrix inside, we think that it is a quintet. Okay, it is quintet, and it is quintet says that the neighborhood is 4, isn't it? N plus 1 rule. According to N plus 1, it is the neighborhood for this particular nucleus is 4. And then quartet, the neighborhood is 3. Triplet, the neighborhood is 2. And doublet, the neighborhood is 1. And singlet, the neighborhood is 0. But in fact, if you look at the spectrum inside the 2D picture, the matrix, the quintet, the 5 line is in fact, it is 2 signals which are almost having the same, very close by chemical shift values, very close by chemical shift values. And there, in fact, we are finding 4 contour spots just very close by to each other. And the same thing, if you can look at the bottom picture, it is more clear. When you tilt this spectrum at 45 degrees, you will find a clear spectrum below where the 2 quartets which are overlapping, they are separated here. So that is the advantage of using a 2D NMR, especially rosy spectrum. So the rosy spectrum here, it is used to resolve a multiplet. So the quintet is in fact not a quintet. It is not due to a particular nucleus. It is, there are 2 different nuclei which have very close by chemical shift values, which are unresolved in normal 1D NMR. But now in the 2D picture, they are resolved to a very greater extent. The reason is all the 4 lines or all the 4 signals, contour spots, they're occupying only a single space line on the x-axis. So the x-axis is with reference to delta, which is nothing but frequency. So all the 4 spots, they are one behind the other, isn't it? So naturally, if suppose the 2 quartets, they are coming in 1D NMR, they are present on the x-axis, there is every chance, because of the close by chemical shift values, there is every chance to get overlapped. But here, because the information is now, the information pertaining to J is dragged onto the new axis, isn't it? So the x-axis is having only delta, and the J value is moved down to the, dragged onto the second axis. So naturally, 4-line multiplet means it is not shown as 4-line multiplet, unlike in the 1D NMR. It is shown, it is going on to the second axis. That is the reason why there is a resolution. So this is how the resolution takes place, and this is what is the advantage. So you will have to look into only the matrix students, that we have to take care. And now I'll give you some specific examples here so that you'll be more clearly understanding. So here, the pyrrole 2-carboxylic acid proton NMR spectrum in deuterium oxide. The left is the normal conventional NMR, that is proton, that is 1D NMR. And to the right, I have drawn, it is not to the scale, you can understand. Only thing is I'm trying to make you visualize the difference between these two. This is 2D NMR. So you all know this is a AMX pattern. That means this particular molecule exhibits the AMX pattern. And since it is the spectrum is taken in deuterium oxide, the NH proton and CO2H protons being labile, they are not detected, and you have only 3 different protons. One is A, M, and X, and A couples with M, and A also couples with X. So you are finding A double doublet. Double doublet means 4 lines. First, it will couple with M into a doublet, and again it will also couple with X. So each line of the doublet is again split into a doublet. So you will have 4 lines, so which is called as a double doublet. And similarly, M couples with A and it is also coupled with X, so it is a double doublet, and X is also a double doublet. So this particular spectrum in 2D NMR, see how it looks. Very clearly you are finding the 4 spots for A. So that means you are finding 4 spots means what? 4 lines. So it is nothing but a double doublet or a quartet. And then M is also a double doublet and X is also a double doublet. So the spectrum is very neat here. Whereas here onto the left, the 1D NMR, the signals are little clumsy because of the close by chemical shift values and the multiplets, because it is a 4-line multiplet. All the signals, 3 signals there, each is a 4-line multiplet. So that is the advantage of ROSI. So like this, you can take any other example and try to understand the ROSI spectrum. So that is what is about homo-ROSI. Now let us come to hetero-ROSI or heteronuclear 2D J-resolved spectroscopy. And this is, as I said, the x-axis refers to the chemical shift values of carbons, and the y-axis represents the couplings between carbon and proton. So here we are finding carbon and proton. There are 2 different nuclei. So it is heteronuclear coupling. So hence it is 2D hetero-ROSI. So naturally, what is a conventional NMR? This is nothing but we are referring to conventional C13 NMR, and we are trying to see this in the 2D picture, isn't it? So it separates the overlapping multiplets in proton coupled C13 NMR. In proton, and this is more advantageous. This particular hetero-ROSI is more advantageous because in C13 NMR, we are going to see the signals of C13 NMR in proton coupled NMR as wide multiplets, broad multiplets, unlike in the case of proton NMR. The reason is in proton NMR, the coupling constants, they vary between 0.5 to 20 hertz. So the multiplets are very narrow. Whereas when it comes to C13 NMR, the coupling between carbon and proton is very high. It is around 50 to 250 hertz. So then naturally, the multiplets, when you compare the multiplets in C13 NMR and the multiplets in proton, the multiplets in C13 NMR are very wide, whereas the multiplets in proton are very narrow. So there is every chance that if the multiplets are wide apart, since the space occupied by a single multiplet itself is large, because the coupling constant is very high, isn't it? So there is every chance that the multiplets getting overlapped. So that, and in fact, this particular J-resolved spectroscopy is more useful with respect to C13 NMR. And next, there are several ways of recording hetero-ROSI, and the simplest is gated decoupled method. So in gated decoupled method, it is nothing new. It is only thing is we have a provision in the spectrophotometer for the decoupler, where the decoupler can be switched on or switched off according to the requirement. So the pulse sequence here, we are showing, unlike in the homo-ROSI, we have shown only one channel. So because it is homo, we have given irradiation only in one channel, that is proton. Whereas when it comes to hetero-ROSI, because it is C13, hetero is always in 2 channels. On the top, we are finding the channels with respect to proton, and in the bottom, it is with respect to C13. So we have to irradiate the sample twice. Okay, one with respect to proton and other with respect to C13. And how is the spectrum seen? So for example, we are talking about this particular 1,2,2 trichloropropane. So in 1,2,2 trichloropropane, hetero-ROSI is nothing but C13 NMR, isn't it? It is a conventional C13 NMR. Only thing is we are trying to see in the 2D picture. Okay, it is a 2-dimensional NMR. The normal C13 NMR, if you refer CH2, which is the downmost signal here, the B signal. I have labeled the signals here, the carbons. The central carbon is B, and then CH2Cl is C carbon, and CH3 carbon is A. So, and here in C13 NMR, since the coupling is between carbon and proton, then again the multiplicity is based on n+1 rule, but here the n here is the number of attached protons. So suppose if you are referring to CH2 carbon, so the number of protons attached to CH2 carbon are 2. So that carbon is seen as a triplet. And if you are talking about a quaternary carbon, since it doesn't have any protons, it is seen as a singlet. And if you are referring to CH carbon, since it has got only one attached proton, it is seen as a doublet. And if you are referring to CH3 carbon, since there are 3 protons attached to it, it will be seen as a quartet. And in fact, carbon NMR, C13 NMR gives a more reliable information compared to proton, because it gives a direct evidence for the skeleton of the carbon. Direct. Suppose if you find a triplet, it means what? It is a CH2 carbon. If you find a quartet, it means what? It is due to a CH3. Whereas proton NMR is always giving an indirect evidence for a carbon skeleton. So naturally, C13 is giving us a more valuable information compared to proton. But to record C13 NMR, there are more difficulties involved. The reason being, it is insensitive nucleus. The reason is the abundance and the magnetic behavior. So the natural isotope of carbon C12 is non-magnetic, and the other isotope C13 is only magnetic. So we can, if at all we want to record carbon NMR, it is only C13 what we get. And if you take, for example, methane molecule, if you take 100 molecules of methane, only 1 out of 100 molecules will be present as C13. So definitely it has got inherent difficulty in recording. So now let us come to heterorosy. So this heterorosy spectrum, the downmost signal is central carbon. So since there are no attached protons, it is just seen as a single spot. And then CH2 carbon, since there are 2 protons, it is seen as a triplet. And then CH3 carbon, since it has got 3 attached protons, it is seen as quartet. So this is about heterorosy. And I'll just deal about some more examples for heterorosy. And all these are not according to the scale. In fact, I have drawn. Only thing is to make you understand. So don't bother about the chemical shifts. You just bother about the nature of the signals here. And the delta values, we are not bothered, but the gradation, I'm showing the gradation in their chemical shift values. So on to the left, you have the furic acid methyl ester. So you find how many signals, how many signals you find. This is C13 NMR. So C13 means number of non-equivalent carbons. How many are there? So there are 6 carbons. So you have to get 6 carbons, 6 signals. So the downmost signal you all know is carbonyl. So C2 is carbonyl. And next is C2, because there are no attached proton. It is a carbonyl, ketonic carbonyl. In the C13 NMR, C is seen as a singlet. Proton coupled C13 NMR, ketonic carbonyl is seen as a singlet, whereas aldehydic carbonyl is seen as a doublet, because aldehyde is CHO, it has got 1 attached proton, doublet. And then C2, then C6. C6 is next downfield. C6 carbon has got 1 attached proton, so it is CH carbon, so doublet. And then C3 is again a quaternary carbon, so singlet. Then C4 is again a CH carbon, doublet. C5 is again a CH carbon, doublet. And last is methoxy carbon, because it is CH3, there are 4 signals. Similarly, onto the right side, you are finding the geraniol molecule. This is a natural product. This is a terpenoid. So geraniol molecule. So again, there are 10 different carbons. So there are 10 different carbons. And the downmost signals are due to 3rd and 7th carbon. 3 and 7 because they are quaternary carbons. So quaternary carbons means there are no attached protons. So you are just seeing them as single spots. And then 2 and 6 are methane carbons, CH carbons. Methane means CH. So they are seen as doublets. So only in the matrix you'll have to observe. On the top, for reference, I have drawn the C13 NMR. And next is 145. All 145 carbons are methylene carbons, CH2 carbons. So they are seen as triplets because CH2. They have 2 protons. And next 9, 8, 10, all are methyl carbons. So hence they are seen as quartets. Okay, so this is how you just can analyze heterorosy spectrum. So heterorosy is nothing but C13 NMR. Homorosy is nothing but proton NMR. So the only thing is the conventional proton NMR and the conventional C13 NMR we are trying to see in the form of a 2D picture, where we are trying to find out a more resolution. The overlapping multiplets are getting resolved. And now coming to the COSY spectrum. So COSY spectrum is nothing but a correlation spectroscopy. So correlation spectroscopy means we are trying to find out correlation. We are trying to find a relation between different nuclei. So it is connectivity. These are nothing but connectivity diagrams. And again, always in the NMR spectrum, whether it is a C13, a proton NMR, any kind of NMR, phosphorus 31, nitrogen 14 or 15, chlorine 19, whatever NMR you are referring to. The information what you're getting from the NMR spectrum for a different nuclei, the signals are split, isn't it? The signals are split based on the environment. That means based on the neighborhood. If suppose we are trying to identify a particular nucleus, the neighborhood, how is the neighborhood influencing that particular signal, is reflected in the form of a multiplet, okay, or multiplicity. Suppose you are finding a quartet. What does it mean? The neighborhood is 3, because always the multiplicity is based on n plus 1. N is neighboring. Okay, so if at all you are finding a multiplet in the NMR, it means what? It means that particular nucleus, whatever nucleus we are identifying or we are detecting, trying to detect, is having a neighborhood. Then only it is seen in the form of a multiplet. Suppose a particular signal is just seen as a singlet. What does it indicate? It indicates that it has no neighborhood. So the interaction in the NMR spectrum is nothing but uh, uh, the neighborhood, or it is in coupling interaction. So the coupling interaction is reflected in the form of multiplicity. So if a particular signal is seen as a multiplet, then we can say it has got a neighborhood. And if it is not seen as a multiplet, there is no neighborhood. And that is what we have seen so far in the rosy spectrum. So the signals are seen as multiplets. So based on the environments. Now the same information we are seeing, trying to see in a different way. Instead of seeing them as multiplets, the coupling interaction, instead of being represented in the form of multiplicity, it is represented by cross peaks. So we are trying to show the connectivity not in the form of multiplicity, but in the form of cross peaks. So it is a different way of representing uh, the what multiplicity, or it is a different way of representing the interaction between the nuclei. So the interaction means coupling again. So coupling is of different types. What are the different types of couplings? What we have observed again, homonuclear couplings and heteronuclear couplings. So homonuclear couplings we observe only in proton, especially if you're talking about if we restrict ourselves to proton and C13. So homonuclear couplings are seen in proton NMR, and heteronuclear couplings are seen in C13 NMR. So homo-cozy, again, there are two types in cozy. One is homo and the other is hetero. So homo-cozy means proton and hetero-cozy means C13. So since we are saying that there is no coupling information, it is only the coupling, it is only the chemical shift information which is seen on both the axes. So X is delta and Y is also a delta. Okay, X axis is delta and Y axis is also delta. So as I told in the very beginning, when we talked about different kinds of 2D NMR spectrum, I said the X axis is always chemical shift and the Y axis is either J or coupling information. Sorry, either J or again chemical shift information. So here in this case, cozy spectrum, so X and Y are referring only to the chemical shift values or chemical shift information. So this is in broad. So again, this is of two types, as I said, homocozy and heterocozy. So we'll just see homocozy. So homocozy is, again, it is useful for complex organic molecules, wherein it gives the proton-proton connectivity through cross peaks, not in the form of multiplicity, as I said. It is seen in the form of cross peaks. That means if suppose the two protons are coupling, normally in rosy spectrum, how do we know that these two are coupling? Naturally, they have to be seen as multiplets, isn't it? But in cozy spectrum, there are no multiplets, but we find a connectivity between these two. And what is that connectivity? A cross peak. So suppose you find a cross peak connecting these two, then we can say these two are coupling. If there is no cross peak connecting these two, then we can say there is no interaction between these two. They are not interacting. They are far away. They are not connected through bond. Okay. So in this homocozy, the x-axis is proton and y-axis is also proton. That means on both the axes we are drawing only the proton NMR, and only the matrix shows the 2D picture. So if you just look at the x or the y-axis, so this is a pulse sequence, students. This is a 90-degree pulse again, and again 90-degree pulse is given, and immediately the detection is carried out. So this is how the spectrum looks. So finally, after the pulse is given, the spectrum is looking like this, and you have two different types of peaks. You find diagonal peaks which are present on the diagonal line. So this is an imaginary diagonal line. So, and on the diagonal line, imaginary diagonal line, you find peaks which are called as diagonal peaks. And symmetrically placed above and below the diagonal line, you find off diagonal peaks, or which are also called as cross peaks, which show the connectivity between these two diagonal peaks. So we find cross peaks only when these two protons are coupling. When they are interacting, then only you find a cross peak. Otherwise, you don't find a cross peak. Okay, so here the diagonal peaks spins that do not exchange their magnetization, and then off diagonal peaks spins that exchange magnetization due to coupling. They give cross correlation peaks. And if you just look at the diagonal peaks, if you take any of the diagonal peaks, so for example, on the diagonal line, you're finding two spots, isn't it? Two peaks. So those two peaks, see on the x-axis, we have drawn a proton NMR, and the same way proton NMR is also shown on the y-axis. So the downmost signal onto the left, the reading goes like this, from right to left. Okay, left is downmost, high delta values. Right is low delta values on the x-axis. And on the y-axis, if you go down, bottom is high delta values, top is low delta values. So accordingly, B is having high delta value, and A is having low delta value. It is upfield and this is downfield. So if you talk about the diagonal peaks, I'll tell you one thing. Diagonal peaks. So if you just look at any one diagonal peak, so for example, I'm talking about the the peak on the diagonal line, the bottom peak, that is B. So that is equal to x-axis and y-axis. X-axis we calling it as F2, and y-axis we call this as F1. So F2 equal to F1. Okay, F2 equal to F1 equal to either, here B we are referring, isn't it? It is equal to B. Whether you read the value on the x-axis or whether you read the value on the y-axis, the delta value, it is the delta value of only B. Okay. And similarly, if you just talk about the diagonal peak on the A, it is equal to F2 equal to F1 equal to delta value of A. Okay. But if you refer to the off diagonal peaks, any of the off diagonal peak, for example, I'm talking about the off diagonal peak which is present above the diagonal line. So that particular peak, if it is we are referring to, it is equal on the F2 axis. F2 means x-axis. On the F2 axis, it will refer to the delta value of B. But on the y-axis, it will be the delta value of A. Isn't it? They're different. But again, if you refer to the off diagonal peak, which is below the diagonal line, on the x-axis, it is B. Okay. Sorry, A. And on the y-axis, it is, on the x-axis it is A, and on the y-axis it is B. So it is different. So now we are finding the diagonal peaks. Since they are connecting these two peaks, A and B, then only you find the cross peaks. Unless and until these two don't couple, you don't find a cross peak, isn't it? So that is the difference between a rosy and a cozy. So rosy is the connectivity is shown in the form of multiplets, whereas cozy, the connectivity is shown in the form of cross peaks. So there are two here. There are only two protons, and the two protons interact. So you find only one peak. And always the cross peaks, the number of cross peaks in a cozy spectrum is according to n minus 1. If suppose there are n interacting nuclei, you will have n minus 1 cross peaks. So now I'll explain two examples in specific, one propanol and two propanol. So onto the left, you have one propanol, and onto the right, you have two propanol. So one propanol, there are three different protons, four different protons altogether. One is OH, then CH2 proton attached to OH, and then another CH2, central CH2, and then terminal methyl. So in total, you find four peaks. So you find four spots on the diagonal line. So the downmost signal are the delta value corresponding to the highest value is one proton, that is CH2OH. And next is in between you have OH hydroxyl proton, and then 2 and then 3. So here this OH is coupling to CH2, and CH2 is also coupling to OH. This terminal CH2 is not only coupling to OH, it is also coupling to the adjacent CH2. So you have to find two cross peaks connecting to this CH2, isn't it? One is connecting to OH, the other is connecting to the CH2, second CH2. So naturally you're finding two cross peaks, isn't it? On the off diagonal line, you can draw a box square connecting these two. So first cross peak is with respect to OH, the other is with respect to CH2. Whereas the third one, the CH2 is having only one connectivity, because it being the terminal, it will couple only with the adjacent CH2. So hence the CH3 proton is coupling only to CH2, and you can find only one cross peak there. This is with respect to one propanol. And when it comes to two propanol, 2-propanol. So there are here 2-propanol. How many different kinds of protons are there? There are 3 protons, isn't it? One is it is isopropanol, isn't it? 2-propanol is nothing but isopropanol. So CH3, CH3, they are in the same environment. They give only one signal, and then CH proton. So CH, both the methyls, they give one signal, and then CH another signal, and then OH. So in total, you have 3 signals. So you find 3 peaks on the diagonal line, and you find how many cross peaks, because there are 3 different protons. You have to have n minus 1, 2. So naturally, you're finding only 2 cross peaks, isn't it? So first one is downmost signal is a CH proton, and it is having connectivity to OH, and it is having connectivity to 1 and 3. Whereas 1 and 3 protons, they have connectivity to only CH proton. So you have only one connectivity for that. So this is about the homocozy spectrum of 1-propanol and 2-propanol. So the same information, if you look at the proton NMR spectrum homocozy in homocozy spectrum, in homorosy spectrum, the same is seen in the form of not cross peaks, but we could have seen this in the form of multiplets or contour spots. Only thing we are trying to show it in a different way. This is a cozy. Okay. Next, we move to another technique, heterocozy. So heterocozy is nothing but the coupling interaction between different nuclei, that is carbon and proton, because we have restricted in the beginning itself, we have restricted our discussion only to proton and C13. So when we restrict ourselves to proton and C13, C13 is heteronuclear coupling, proton is homonuclear coupling. So heterocozy means it refers to only C13 NMR. So the chemical shifts of C13 are correlated to the chemical shifts of protons to which they are coupled. So always in C13 NMR, proton coupled C13 NMR, we see only the coupling between directly attached protons. So one bond couplings, short range couplings we observe. Long range couplings are not seen much, and we don't concentrate much. Our main interest is only short range coupling, that is one bond couplings, directly attached protons to the carbons. So x-axis refers to delta values of C13, and y-axis refers to the delta values of protons. And the pulse sequence is given here. So again here, because it being a hetero sequence and heterocozy, we have to irradiate the sample in 2 channels. One is with reference to proton, and the other is with reference to C13. So the top pulse sequence is with reference to proton channels, and the bottom is with reference to C13 channels. So you give different pulses. This is according to the experiment. Different kinds of experiments are there. By manipulating different pulse angles and maintaining time delay intervals, we get different information. So we are not concentrating much on the pulse sequence. The only thing is what is information. So this is a pulse sequence applied in the heterocozy, and the spectrum looks here. Unlike in the homocozy, where you are finding a diagonal line, okay, and then cross peaks symmetrically placed above and below the diagonal line, here slightly it is represented in a different way. So, and for our reference, on the top, that is on the x-axis, we are referring C13 NMR, and on the y-axis, we are referring proton NMR. And in between, inside the box, the matrix only is representing the 2D picture. So here, the heterocozy, it is nothing but, as we said, it is C13 NMR. So for example, if we talk about 2-nitropropane, 2-nitropropane heterocozy is nothing but C13 NMR. How many signals we get? Naturally, we get only 2 signals. So it is 2 methyls are in the same environment. So you get only 1 signal for the 2 methyls and another signal for the methane carbon. So you get 2 signals. So as I said, the cross peaks are according to n-1. So the number of spins, interacting spins are 2, n is 2. So the cross peaks are, so here, unlike in the homocozy, the cross peaks, here it is between carbon and proton. So we have to find the correlation between carbon and proton. So if you just look at the interaction or the connectivity, we have to show the connectivity in such a way that, the connectivity is shown in such a way that if you draw a line vertically from the carbon signal, respective carbon signal, and extend it to the y-axis horizontally, it will meet a particular proton to which it is coupled. Okay, so here we are finding downmost signal is second carbon, which is very, very small, which is not seen very clearly. The reason is on the x-axis we are referring to C13. As I said before, C13 is very insensitive. The signals are also seen with very less intense, and that too it is CH carbon. So CH3 carbon is seen with more intensity compared to CH. So CH is seen with very less intensity. So on to the left, we are finding CH carbon, that is 2, labeled as 2. And on to the right, okay, that is 1,3 carbon with little more intensity. So now if you just draw a line vertically from the second carbon, so on the diagonal line, imaginary diagonal line, you are finding an orange dot, isn't it, where at the corner. So that vertical line, from there, if you draw a horizontal line, it will meet a point on the y-axis, which is connecting the second proton, that is a CH proton. This on the x-axis, it is CH carbon, and on the y-axis, it is a CH proton. So there is a connectivity between this carbon and this proton, because this is a head core spectrum. Heterocozy is nothing but head core spectrum. It is head core spectrum means it is nothing but C13 NMR. 2D picture. C13 NMR means coupling between carbon and proton. So this particular methane carbon couples with that proton which is present directly onto this. So that is nothing but a CH proton. So hence we are finding a connectivity between these two. This is what is called as a cross peak. And similarly, if you come to the rightmost signal, 1,3 carbon, if you draw a line from below 1,3 signal into the matrix, and then extend it to the y-axis horizontally, at the corner there is a cross peak which is shown in the orange dot, in the form of an orange dot. So now it is showing connectivity between 1,3 carbon, that is CH3 carbons, to CH3 protons. So because it is a heterocozy spectrum where you are trying to show a connectivity between carbon and proton. So this is what is called heterocozy. And then another example for heterocozy, which is in fact a little complicated spectrum. This is isopentyl acetate. Isopentyl acetate. So there are 6 different carbons here in this isopentyl acetate, and here 6 different signals. I am not showing the fifth carbon. Fifth carbon is nothing but carbonyl, and carbonyl doesn't have any attached protons. So if it doesn't have any attached protons, it will not definitely have any cross peak, because it will not couple. Since it has no directly attached protons, it will not couple, and hence it will not have any cross peak. So I have not shown that. So on the x-axis, you see on the top, it is a conventional C13 NMR. So the delta values are accordingly. The 4th carbon is downmost signal. Next is 3rd carbon. Next 2nd carbon. Next 1st carbon. Next 6th carbon. This is C13 NMR delta values. And if you refer to the y-axis, proton NMR spectrum is given. The delta values are slightly different. The gradation is slightly different. So here in proton NMR, the 4th proton is more de-shielded. So 4th proton is seen downfield. Next is 6th proton, and next is 2nd proton, next 3, next 1. Okay. So now we'll see the connectivity. So we'll start with C13. So the 4th signal, the 4th carbon, it should have a connectivity in the matrix. If you look into it, matrix, since it is head core spectrum, and head core spectrum is nothing but the conventional C13 NMR. So the CH2 carbon means the carbons are coupling only to the protons to which they are directly bound. Okay. So 4th carbon to 4th proton. So now if you just look at, if you draw a line vertically from the 4th carbon signal and extend it to the y-axis by drawing a horizontal line, at the corner you have a cross peak. That means the 4th carbon is connected to 4th proton. And next is 3rd carbon to 3rd proton, 2nd carbon to 2nd proton, 1st carbon to 1st proton, 6th carbon to 6th proton. Okay. Now, in fact, when you are looking into the head core spectrum, you don't bother about the multiplicity of proton NMR on the y-axis. So y-axis is conventional proton NMR, and the matrix here is 2D picture, which is C13 NMR. So the y-axis proton NMR, what we have shown is according to its coupling, that is homonuclear. We not bother, only the center one, the matrix inside, we have to bother. So the matrix here is representing C13 NMR. So we have to have a correlation between carbon and proton. So C4 carbon to H4 proton, C3 carbon to H3 proton, C2 carbon to H2 proton, C1 carbon to H1 carbon, C1 carbon to H1 proton, and C6 carbon to H6 carbon. So this is about the hetero-COSY spectrum. And next we'll discuss about TOXY. TOXY is nothing but total correlation spectroscopy. So total correlation spectroscopy, unlike the previous, till now we talked about correlation spectroscopy, where we have confined only to a spin system. That means, for example, if you have a spin system, ABCD spin system, and in this ABCD spin system means, so ABCD means four different nuclei are there. And always TOXY here we are referring to means it is with reference to HOMO, that is proton. We are referring to only proton in NMR. So TOXY we are referring to proton. So HOMO nuclear couplings only. So if you have a spin system like ABCD, so ABCD means 4 different protons, A, B, and C, and D. So in a system ABCD, if we are referring to A will have how many interactions? It will have one interaction because it is immediately connected to B. So it will have connectivity corresponding to A and B. And B will have 2 because it is center. It will have connectivity to A as well as to C. So with respect to B, you will have 2. With respect to A, you will have 1. And with respect to C also, you will have 2 because C will have connectivity to B as well as to D. But again, when it comes to D will have only one connectivity. It being the terminal one, it will have connectivity only to C. So this is normal COSY spectrum. But in TOXY, total correlation spectroscopy, each nucleus, okay, will have interaction with every other nucleus. So because in this ABCD system, there are 4 spin systems, 4 spins. So N is 4. So what is N minus 1? 3. So normal COSY means you will have only in the total molecule, you will find only 3 cross peaks. But whereas in TOXY, okay, see, I'll show this. Yeah. COSY versus TOXY. Onto the left, you have COSY, and to the right, you have TOXY. So here you just count the number of spots on the diagonal line. So the diagonal line, the green dots are representing different spins or different nuclei. So how many are there? There are 5. So 5 interacting nuclei are there. So how many? N is 5. So how many cross peaks you will have to find? 5 minus 1, that is N minus 1, 4. So in COSY, you will have to have in total 4 cross peaks. So the red dots are cross peaks. So above and below you are finding, and you are completing a box, isn't it? So the both represent one cross peak. Okay. So how many such are there? 1, 2, 3, 4. There are 4, isn't it? That means since it is a spin system 5, so you are finding N minus 1, 4 cross peaks. Whereas in TOXY, each nucleus will have N minus 1. So each nucleus will have N minus 1 means 4 because there are 5 interacting nuclei. So you will have each, for example, the downmost dot, if you consider green, how many cross peaks are there for that? 1, 2, 3. Okay, 1, 2, 3, 4. Similarly, the second one, again you have 4. Third one, again you have 4. Third one is 2 above and 2 below. Fourth one, 1 above, 3 below. And last one, fifth, all the 4 below. Okay, so this is what is TOXY. So TOXY is total correlation spectroscopy. So in a chain of a spin system, if suppose there is no interruption, you find all the correlations, and that is what is called total correlation spectroscopy. So this is the advantage of TOXY over COSY. And here there is an example, 3-heptanone. And here 3-heptanone, there are 2 spin systems here, students. On either side of the carbonyl, you have 2 spin systems. On to the left, you have ethyl spin system, CH2, CH3. And on to the right side of the carbonyl, you have a butyl spin system. So you have CH2, 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 and CH3. But here, both the spin systems are interrupted by a carbonyl. So the carbonyl here is a culprit. It is interrupting one spin system from the other spin system. So it is called a quaternary center is called a spectroscopically silent. So it is not allowing to relay the information from one spin system to another spin system. So even in TOXY, you will find the total correlation only with respect to 3, 4, 5, 6 because it has no connectivity to other ethyl system. So in 3, 4, 5, 6, you will have, for 3, you will have 3 connectivities, 4, you will have 3 connectivities, 5, you will have 3 connectivities, and 6, you will have 6 connectivities. And for ethyl, you will have, for 2, you will have 1, and for 1, you will have only 1. So this is on to the right, the toxic spectrum, and to the left, you have COSY. And I have not shown the boxes, because if I show the boxes, it will become too clumsy. Only thing is, students, if you want, you can refer this diagram. And if you just sit coolly and try to draw the diagram, complete the boxes, you will find all sorts of interactions, what we have seen previously like this. You'll get all boxes here, like same thing. So this is with respect to 3-heptanol molecule. So this is COSY versus toxic. Next, we'll move to 2D inverse detection techniques. So what do you mean by inverse detection techniques? The name itself is indicating that something which is reverse, something which is just opposite. And here in 2D NMR techniques, it is everything is with reference to X and Y axis. So the information pertaining to X-axis, what is the information we are getting on the X-axis, and what is the information we are getting on the Y-axis, isn't it? So this inverse techniques, definitely it will restrict ourselves to heteronuclear couplings, because in homonuclear couplings, it is only proton-proton. So there is no question of inverse detection technique applying to homo. So the inverse detection technique is applicable only to heteronucleus. So it will provide the same information as that of HETCOR, and it is for better resolution. So inverse techniques, why it is called better resolution? In normally in HETCOR spectrum, that is heterocosy, we have seen the x-axis is occupied by C13 chemical shifts and the y-axis is occupied by proton chemical shifts. And if you have seen earlier in my spectra, what I have shown, you have seen the resolution, that is the spectrum, y-axis spectrum, the proton NMR spectrum is shown in the form of multiplets, whereas the C13 NMR is shown in the form of only the x-axis. We are not talking about the matrix inside. It is shown only in the form of singlets, irrespective of the attached protons, whether it is a quaternary carbon or a methyl carbon. All the carbons are seen as a singlets only, because we had referred to only proton decoupled C13 NMR. So always C13 means, if you don't specify the kind of C13, it is only the proton decoupled C13 NMR. And here, that means where is the resolution much required? The resolution is required more when you find multiplets. The resolution is less required when you don't find multiplets. But in x-axis, C13 NMR, there are singlets. Y-axis, there are multiplets, that is proton NMR, where more resolution is required. Okay, but the x-axis information is obtained when, how is the x-axis information obtained? When you do FT over T2, that is first FT over T2 is giving the information pertaining to x-axis. So now if you interchange the axis, so y-axis information, if you get to the x-axis, that is proton information if you get to x-axis, and the y-axis information, that is x-axis information if you get to the y-axis, then the resolution what we need in the proton is now applicable to the x-axis, because it is the first FT. First FT means more resolution. So this particular based on that particular concept, these inverse techniques are developed, in fact, and these are recently developed. Suppose had these been developed before only, the normal HETCOR would have been called as inverse technique, isn't it? So these give better resolution compared to the normal HETCOR. And there are again two types. One is heteronuclear multiple quantum coherence, that is HMQC, where you are going to find direct couplings, that is HETCOR spectrum, what we have seen, one bond couplings, CH direct couplings, one bond couplings. And heteronuclear multiple bond coherence, that is called HMBC, where neglecting one bond couplings, you find 2 and 2, 3 and 4 bond couplings. Sometimes 2, sometimes 4 bond also is observed. So normally we don't observe any direct couplings. We observe only 2 bonds and 4 bonds, which is not of much use. We'll restrict only to HMQC. So HMQC is nothing but HETCOR. Only thing is we are seeing, instead of seeing x-axis on the C13 on the x-axis, we see C13 on the y-axis. So I'll just show comparison between head core and HMQC. So onto the left, you find HMQC, and onto the right, you find head core. See, the matrix, the appearance of the matrix is same. So it is the same C13 NMR, 2D picture of C13 NMR, conventional C13 NMR. So the example here is 1-nitropropane. So 1-nitropropane means how many carbons are there? There are 3 different carbons. So you have to find 3 different signals. So HMQC, so 3 different protons. One proton is downfield. It is a triplet because it proton NMR, the coupling is homonuclear. So it is seen, one proton is seen as a triplet because it is coupling to the adjacent CH2. And the second proton is seen as a multiplet because it is coupling to CH3 and CH2. And the third proton is again a triplet because it is coupling only to a CH2. And if on the y-axis, if you observe, we have drawn only the decoupled spectrum, C1, C2, C3. And in the matrix, the connectivity is between carbon and proton. So proton, H1 proton to C1 proton, H2 proton to C2 proton, H3 proton to C3 proton. Similarly, head core, we know already, C13 x-axis and y-axis proton. So the same thing, the matrix is same thing. Okay. So it is, see here the points are given. HMQC is aimed at enhancing the signal due to sensitive nucleus. What is the sensitive nucleus here? Proton. Whereas it is, head core is aimed at enhancing the signal due to insensitive nucleus. So how do we achieve this? In HMQC, initial pulse and detection occur in the sensitive channel. Isn't it? Isn't it? That is T2. While the evolution period is detected in the insensitive channel. That is the reason why the information pertaining to x-axis will refer to proton in HMQC. Okay. Whereas in head core, initial pulse and detection occur in the insensitive channel, that is C13. Hence, it will move to the this insensitive will move to the x. In head core, it is moving. It is on to the x-axis, and the sensitive channel is the y-axis. Okay, so this is the difference between HMQC and head core inverse techniques. Okay, so this is the direct bond couplings. So we are finding only one bond couplings. We are trying to see only the one bond couplings. I am not showing any two bond couplings. Okay, now so far we discussed about through bond connectivity. We have discussed about only through bond couplings or through bond connectivity. So far, whatever we have discussed, whether it is ROSI or COSI, or inverse techniques or TOCSI, total correlation spectroscopy, it is only with reference to through bond connectivity. When unless and until the protons or the nuclei, whether it is, let us not say protons, because we have discussed even about the C13 number. We have seen the connectivity through bond. Okay, so through bond connectivity will be in saturated systems up to 3 bonds, and beyond 3 bonds it is difficult to observe. Only in unsaturated systems, like if you have double bonds, you can observe allylic couplings also. But here the NOSI is the spatial, that is, unlike the through bond connectivity, even we can see the spatial connectivity also. The spatial connectivity, the observation of spatial connectivity is seen in the NOSI spectrum. So this is nothing but nuclear Overhauser enhancement spectroscopy. This is spatial. This is representing the spatial connectivity or through space interaction. So in this, we are not bothered about the coupling interaction. We are bothered about only the spatial connectivity. And this is a stereochemical tool. So the arrangement in space. So naturally, it is stereochemistry. It is called as a more or less through NOSI or NOE technique is used as a stereochemical tool. It is used in the determination of configuration and conformation of the molecules, complex molecules. That is, we can know the geometry of the molecules, the structure of the molecules, the shape of the molecules. So it is useful for determining the protons which are closer in space but not closely connected by chemical bonds. Like for example, in the slide onto the right side, there is a small picture showing where the two protons, HA and HB, the number of bonds in between are more. In fact, it is not clearly saying how many bonds are there, but the number of bonds between them are definitely more than 4 to 5. But in space, because of the geometry, the two protons are coming very close due to the folded shape. So how do we identify that they're coming closer? We can identify this through nosy technique. Provided these two nuclei, there is one condition to observe this nosy. The two nuclei which are coming closer in space should be separated by less than 5 angstroms. If they are separated by less than 5 angstroms, then by applying a special pulse sequence, we can detect this. And how is it detected? How is it reflected in the spectrum? It is reflected in the form of cross peaks again. So the same information what we have seen in homocausi, the same information, the analysis, the appearance is same as that of homocausi, but the information what you're going to get here in nosy is different. Spatial proximity shows the spatial proximity between the protons, provided the two protons are coming closer in space within 5 angstroms distance. The number of bonds separating them may be more. They don't couple, but being closer in space, you can say the connectivity in the form of cross peaks. And this is the pulse sequence. It will have an additional mixing time here. And the second 90-degree pulse is very important. It depends upon the size of the molecules, how much duration we have to give. Depending upon the size of the molecules, the mixing time varies. So here, the spectrum is shown in the form of a box here, the matrix. So the diagonal peaks, blue dots are the diagonal peaks. There are two interacting nuclei. Interacting in the sense here, spatially interacting nuclei. And the two diagonal peaks are having cross peaks, which are shown in the form of dots, red dots. They are having a cross peak, indicating they are closer in space. That means their distance in space is within 2 to 4 angstroms. That is the reason why we are finding a cross peak. So the nosy spectrum here contains diagonal and cross peaks similar to COSY, but nosy cross peaks are weaker than those observed in COSY. And the diagonal peaks correspond to normal 1D spectrum. The cross peaks indicate the NOE effect between different sets of protons. So now I'll just take how this particular nosy is useful. This is a very important stereochemical tool, which is very, very important in order to know the structures of the molecules. Sometimes what happens is the NMR spectrum, the proton NMR spectrum of two molecules, for example, cis and trans isomers we talk about. The NMR, proton NMR spectrum of cis and trans isomers look alike except with respect to J values. And the rest of the thing, they are same. But with respect to nosy, their spectrum differs a lot. So in order to know the difference, whether the spectrum is due to a cis isomer or due to the trans isomer for simple molecules, with respect to J values, we can confine, we can understand. If the J value is between 11 to 14, we can say it is a cis compound. If it is more than 14, that is around 17 hertz, then we can say it is a trans isomer. That is applicable for simple molecules. We can apply this to simple molecules and analyze whether the spectrum is due to a cis isomer or a trans isomer. But when it comes to complicated molecules like here, the bicyclic lactone is here given, where because of the geometry, see, as I said, if the molecule is linear, okay, if the molecule is linear, the protons, like for example, let us say the previous example, let me explain more clearly with respect to this, and then I'll confine to the specific example. In this molecule, A and B are coming closer because of the geometry. If suppose the molecule is spread like a rope, okay, one end of the rope will be occupied by A and the other end of the rope will be occupied by B, where there are more number of carbons in between, where A and B are connected by more than 3 or 4 bonds. So definitely they do not couple and there is no connectivity between A and B. But if the molecule, instead of a straight rope, let us, if you consider it to be a bent rope, then automatically they come closer, isn't it? So if whenever you have a structural ambiguity regarding the molecule structure, whether it is adopted, whether it has adopted a linear shape or a folded shape or anything, we can know through nosy. So similarly in this molecule, this bicyclic lactone, here I have highlighted some of the protons. The vinyl proton, 9 proton, if you observe, it has got connectivity to H1 and H8A. So cis fusion. So this is a bicyclic lactone where there are two cyclohexane rings fused together. And you all know that two cyclohexane rings fused together gives a decalin system. And decalin system, trans-decalin, cis-decalins, you all know it. And cis-decalin, this is a cis-decalin system you can consider. and the ring junction protons. So the ring junction, on the A ring, you have a vinyl system, and on the below, you have the same thing, you have 8A proton. See, the vinyl proton and 8A proton, if they are cis fused only, they are coming closer. Both are beta, isn't it? They're coming above the plane. If suppose it is trans, one will be above, the other will be one will be above and the other will be below. So they are far apart in the space. Okay. Whereas in cis fusion only, these two will be in the same plane. That is, both are in the above plane here. It is shown. Both are beta, both are above, and that is shown in the form of a cross peak. So if you just see the matrix here, the noisy spectrum, H9 is having connectivity to H1, brown one, 4.17. Similarly, it is showing connectivity to H8A, which is at 2.32, brown line, the cross peaks. So you're finding cross peaks. So you're finding cross peaks. The H9 is having cross peak to H1 and to H8A only because if the molecule is only in this conformation, you can find a connectivity cross peak. Otherwise, you wouldn't have seen a connectivity. Similarly, it is further highlighted that the molecule is cis fused only in this system, that H1 prime and H5 protons, green protons, H1 prime and H5 protons. They're again closer. See, they are shown in the form of green lines. See, 1 prime and 5 prime. And similarly, 8A proton, it has got the connectivity. It is coming closer to H4 and H5 also. So blue, they are blue connectivities. They're shown. Everything is shown in the matrix form. So this is how you can rule out whether the lactone, bicyclic lactone here is cis fused or transfused. Only in cis fusion, the vinyl and the 8A proton, they are in the same plane. They're coming above. And only when they come above, you find a cross peak in the noisy spectrum. So this is how you can just look at the noisy spectrum. And one more very important thing is, how is it useful in biology, the applications? So this particular noisy technique, as we are saying, it is a stereochemical tool which is used in finding out or determining the secondary and tertiary protein structures, especially, let us say, the alpha helical structure, we can say. Normally, the 3D picture of proteins is known, determined using X-ray crystallography, XRD. But unlike that, even with the help of NOSI also, we can find out. How is it? See, the proteins, they are nothing but they are polypeptides, isn't it? They are formed due to the linkage of many amino acids. And they are taking up this, the secondary structure of proteins is because of the alpha helical structure is because of the internal hydrogen bonding possible. If you just look into the structures here, beta pleated sheet, and then the alpha helical structure is given. The blue lines which are shown are hydrogen bonding. So the molecule is able to adopt this structure because of the internal hydrogen bonding. That is the reason why instead of taking a linear shape, the polypeptide chain, which we are calling is nothing but a protein chain. If it is a linear, okay, and if it is a folded shape like alpha helical structure, which I have shown here, why it has to take up the linear shape, take the folded shape, unlike the linear shape, because of the internal hydrogen bonding. So because of the internal hydrogen bonding, it acquires extra stability, and hence instead of taking a linear shape, it is taking, or it is adopting this particular folded shape. And now, based on this, how is it useful and how is it linked to our nosy? Because of this, what is happening is the protons which are far away in the amino acid residues, if suppose the protein chain is linear, they now come closer in space because of the helical structure. And how is it identified in the NOC spectrum? In the form of cross peaks. So if suppose the amino acid residues which are present, the peptide links, the peptide links are formed, and then we are saying the hydrogen bonding is formed between CO of one peptide and NH of another amino acid, which is around 4th or 5th amino acid peptide. So they are informing hydrogen bonding, and that is how the molecule is stable, isn't it? So now the residues which are present, the amino acid residues, the protons will be present in that amino acid residues, isn't it? Those protons, they come closer because of this folding shape, the alpha helical structure. And the protons, the amino acid protons, which are present elsewhere around fourth or fifth amino acid, they will come closer in space and you find cross peaks. So here, in fact, I have not, I didn't get any such spectrum. So I'm just trying to represent here like this. Like for example, here there are groups here, blue, red, and green balls. Okay, beads. Let us say the beads are there on the chain. So on the top it is a linear shape, and on the bottom it is folded. So green beads, they are far away. Red beads, they are far away, and blue beads are far away in a straight chain. But if suppose the molecule is adopting a folded shape, what is happening? The distance is not, the number of bonds is not changing. It is remaining the same thing. But when due to this folded shape, they're coming closer in space. And if the space is between 2 to 4 angstroms, automatically you find a connectivity. And that connectivity is identified in the noisy spectrum. And that is what is happening in the noisy spectrum of the proteins. And that is how we have identified that the proteins are not linear. They are acquiring the folded shape, that is either alpha helical structure or the beta pleated shape. And that is because why is so? Because of the internal hydrogen bonding. That is nothing to do with our nosy, but we are able to identify with the help of nosy, with the help of cross peaks. So this is how the nosy spectrum is useful in knowing the structures of the proteins, especially in biology. Bigger molecules, very complicated molecules with respect to geometry, cis trans isomers, configuration, conformation, and so on. Okay. So last thing which is left over is the uh, technique which is called as 2D inadequate. We are dealing this at the end. The reason is this is the most powerful technique. So unlike the techniques what we have discussed so far, it is useful in cases where if suppose a molecule is interrupted by a spectroscopically silent regions. As we said, what are spectroscopically silent regions? Quaternary carbons, isn't it? So in such cases, we can make use of this technique, and we are calling this as a most powerful technique because here in this technique, we are trying to find connectivity between carbon and carbon. And carbon and carbon means in NMR, we should not say that it is the connectivity between carbon and carbon, because NMR means nuclear magnetic resonance. It is with reference to nucleus. So it is not at the atomic level, it is at the nucleus level. So nucleus means definitely we'll have to refer to which isotope of that particular atom of an element. So we'll have to say whether it is C12 carbon or C13 carbon. So if we come to carbon, carbon has isotopes like C12, C13, C14. We will not refer to the C14 radioactive isotope. We'll refer to only C12 and C13. So C12 is more abundant and C13 is less abundant, but C12 is non-magnetic because the spin is zero. I is resultant spin is zero. And to get an NMR spectrum for any nucleus or to record an NMR spectrum for any nucleus, that nucleus should be NMR active. It should have a resultant spin. So carbon 12 is useless as far as NMR is concerned, and only C13 is useful because it being magnetic. But the thing is, unfortunately, C13 nucleus is less abundant compared to C12. So the natural isotope of carbon is C12, which is 99%, and this is only 1 in 100 molecules. So if you just want to detect, if you are recording a C13 NMR means we are trying to find out this 1 in 100 molecules of C12. We are trying to detect one molecule, which is of C13. So the probability of finding such a nucleus is very, very less, isn't it? So that is the reason we call it this. We call this as insensitive nucleus. And not only this is called insensitive, not only because of this magnetic, that is magnetic behavior, that is resultant spin, but also with respect to the abundance. The abundant one is magnetic behavior, and the other is the abundance, and the other one is gyromagnetic ratio. So the gyromagnetic ratio of this carbon 13 is very less in compared to proton. So for that reason also this is called insensitive nucleus. And if you are trying to find connectivity between one carbon and another carbon, both the carbons have to be present as C13, isn't it? One cannot be C12 and the other cannot be C13. If one is C12, the other is C13, we don't find any connectivity between them. If you want to find the connectivity between them, definitely both of them should be as C13. So normally to detect one carbon, okay, it is 1 in 100. But if you are trying to find out two carbons adjacent to each other, both of them have to be present as C13. So the probability is 1 in 10,000. So it is becoming more and more less feeble. So it is suffering from incredibly low sensitivity. And even such incredibly low sensitive nucleus we are trying to detect with this particular powerful technique. And hence this is called as a more powerful technique. And the information what we are getting from this particular technique is definitely very useful, because even such low sensitively seen in C13 also we are detecting, means definitely the information what we get derive out of it is very, very useful. And we call this as a more powerful technique. That is the reason why we are discussing this end. For example, if you consider all these techniques what we have discussed so far to find out the structures, if you compare these techniques as tools, and if you compare these as weapons, and if you are moving into the war field with our weapons to fight with our opponents, isn't it? And we use the most powerful weapon only at the end, isn't it? We don't use the more powerful weapon in the beginning itself to fight with what less robust people, isn't we use this technique only at the end. If suppose the person opponent is very strong, then only we use the more powerful weapon, and that most powerful weapon we call it as a brahmastra. So similarly, this is like 2D inadequate is called as the most powerful weapon, like brahmastra. This is a technique or a tool, the most powerful technique. That is the reason why we are talking this at the end, where we are trying to find out the connectivity between the two carbons. So this is a pulse sequence, and here the information. So the information, how is the information shown here? The spectrum of the 2D inadequate spectrum of 2-butanol is given here. So here each carbon, there are 4 carbons. 2-butanol means 4 carbons. This is nothing but C13 NMR. So C13 NMR, there are 4 different carbons. You find 4 different carbons. And the bottom one is exclusively C13 NMR. And only the top one is the 2D NMR, and that too in the matrix form. So you're finding an imaginary diagonal line, and that imaginary diagonal line, so you're finding a pair of doublets on either side of the imaginary diagonal line. And if you consider any one pair of doublet, okay, for example, let us consider C2. C2 has got 2 pairs of doublets, and if you consider any doublet in a vertical line, so in a vertical line corresponding to C2, there are 2 doublets, isn't it? So one doublet, that means 2 doublets indicate that the C2 carbon has got 2 connectivities. So naturally, the C2 carbon has got 2 connectivities, isn't it? It has got connectivity to C1 carbon as well as to C3 carbon. So it has shown 2 connectivities. And how are the connectivities shown? The connectivity between different carbons are shown in the form of horizontal line. Okay. So the horizontal line C2, you have to see connectivity of C2 to C1 on one side and C3 to another side. So if you just look at the pair of doublets which are present equidistant from the diagonal line. So for example, C2, C1. So if you consider the doublet corresponding to C1, that means the C1 corresponding to C1 signal, you find only one doublet, isn't it? Whereas for C2, you find 2 doublets. One is showing connectivity to C1, the other is showing connectivity to C3. So let us talk about C2, C1. C2 and C1. How do you know that they are connected? They are connected, or the connectivities between these two. These 2 pair of doublets are equidistant from the diagonal line, isn't it? And similarly, the C2 is also having connectivity to C3. So if you just come look at the C3 signal, so above the C3 signal, again, you're finding a doublet. So this C3 doublet is having connectivity to C2. So that C2 and C3, they're equidistant to the diagonal line. And if you come to the C4, C4 being this terminal carbon, it has got only one connectivity. It is connecting directly to C3. So C4 is having connectivity to C3, where it is shown top. So C3 and C2 being central ones, they have 2 connectivities. So the number of connectivities a particular carbon is having is shown in the matrix by the number of cross peaks. Okay, sorry, number of pair of doublets lying in a vertical line. So in any vertical line, okay, in any vertical line, the number of doublets you are observing will correspond to the number of connectivities. So how many are there for C3? There are 2. So since there are 2 connectivities. Similarly for C2, how many are there? There are 2 doublets are there, because C2 also has got 2 connectivities. One is to C1, the other is to 3. Okay. Whereas for 4 and 1, there is only, for 4 and 1, there are only one connectivity each, because 4 and 1 are, there are terminal ones. So this is the 2D inadequate spectrum for 2-bit-enol. So this finishes the lecture. 2D NMR techniques, all 2D NMR techniques, different types of 2D NMR techniques, and the concepts behind each 2D NMR. The concept, actually, what is the concept behind the 2D NMR spectrum? So this particular concept or this particular technique has been developed with the intention that the multiplets which are getting overlapped, to resolve the multiplets, okay, which are getting overlapped due to very close by chemical shift values and due to more number of signals, to resolve that, with the intention, this particular technique has been developed, where the information pertaining to the couplings is dragged on to a new axis. So we are resolving the multiplets. With that intention, this particular technique has been developed, and based on that, more and more advanced techniques are being developed nowadays. And you have, apart from these basic techniques, there are many more techniques which are very much useful to know the structures of the molecules. If suppose the structures of molecules are we are unable to solve using basic proton and CTET NMR, then we can take the help of 2D NMR techniques. Depending upon our experiment, depending upon our molecule, you can resort to any of these examples and then explain. So this I have finished. Now you can ask questions. Hello?
Yes, ma'am. Yes, ma'am.
Finished? Sir, is it clear?
Yes, ma'am. You can stop sharing, ma'am.
Clear?
Yeah, clear. Stop sharing.
No interruption. No interruption in between.
Yes, yes.
So I am done. Yes.
Stop sharing.
Okay. Now the references. The students, those who want the references, especially this particular 2D NMR techniques are seen in the case of the best book for 2D NMR spectrum is Ataur Rahman, Nuclear Magnetic Resonance, Basic Principles, Ataur Rahman. And especially not only this Ataur Rahman, the basic principles are present, but also you have one more book called 2D NMR Techniques, written by Ataur Rahman. You can refer to any of these books, and this is more advanced, in fact. And for the beginners, you can refer to Organic Spectroscopy by Pavia, and then Jagmohan, and then Silverstein, and et al. And for knowing the structures of big molecules, natural products, and other things, you can refer to Fleming's and even Silverstein, which is showing the 2D NMR spectrum of complex molecules. So these are the references. Okay. And thank you for patiently listening, all the participants.
Hello, madam. Cheptan, madam.
Ma'am, can you stop sharing, ma'am?
Me? Okay.
Thank you, madam.
Okay.
Very informative session. Thank you very much, madam. Very wonderful session. A clear and concise explanation of 2D NMR techniques. This is very useful for our B.Pharm and M.Pharm students. And also thank to our principal for organizing this webinar series. And also thank to administrators, and thank to everyone who are the part of this session, and with our cooperation, making this session with successful for webinar.
Video on cheyandi, madam.
Nena?
Sarita, madam.
Sarita, check the chat box and ask the questions, ma'am.
Yes.
Please read the questions in the chat box.
Madam, one question is there. Is there enough, like a...
Sarita, not clear.
Hello, madam. These are like MRI. 2D NMR also it will be diagnosed. We can use for diagnosis.
Yeah, we can see MRI is nowadays it is more it is gaining popularity in the medical field because it is the basic principle is only the NMR, isn't it? So instead of using X-rays, instead of getting the body exposed to X-rays because of less energy, so the radio waves are involved, less energy, so they are more less damaging to the body. So MRI is nothing but the basic principle involved in MRI is nothing but NMR. So the same thing is applicable. Hence, it is more useful in fact.
Yeah, Sarita, next. Sarita, any other questions? Are there in the
No,
chat?
no, sir. No, sir.
Okay, that's all.
Okay.
Okay, okay. Thank you, Sarita.
Madam, your video is not moving, ma'am. It is still,
Me-
ma'am.
Myself.
Yes, ma'am.
Okay.
Live
what,
में
what
नहीं
will
है. हाँ, अब live में है.
Now, it's-
Yes.
నేను లైవ్ అంటే నేను చాట్స్ చూస్తున్నా చాట్స్ చూస్తున్నా
ma'am, I have a doubt.
yeah.
One question.
Hmm.
So in signal, you are saying stacked plots. What is the meaning of stacked plots, ma'am? Stacked.
ఏంటి
Stacked plots.
stacked plots. Okay, stacked plots is nothing but the signals are coming above instead of contour spots. The same signals, it can be either represented in the form of contours or stacked plots. That means they are coming 3D picture, they are just coming one they're coming out anamata. That is called, it's called as stacked plots. So 3D picture generally we are trying to show in the 2D form. It is difficult, real pictures kada. So naturally it has to be shown in the only in the form of contours.
What is DEPT, ma'am?
Huh?
DEPT, depth.
DEPT is a distortionless enhancement by polarization transfer technique. This is another multipulse technique which is useful for enhancing the C13 signal. This is C13 is an insensitive nucleus which is used to enhance the sensitivity of the insensitive nucleus, wherein the magnetization has been transferred from the more sensitive nucleus like proton to C13. Like for example, we take remedial classes for the poor students, isn't it? Weak students. How do we attach? Suppose the teacher doesn't have time to deal with the weak students. What the teacher does is, a clever teacher, what he or she does is, she will attach that particular student to a more intelligent student, so that that knowledge will be transferred to this particular weak student if they are attached. So similarly, when you try to involve both the sensitive nucleus and an insensitive nucleus, some of the magnetization or polarization is being transferred from the more sensitive nucleus like proton to C13, so that the carbon-13 signals are seen with more intensity. And in the depth spectrum, it is one of the techniques where such in sensitivity is being enhanced. And in the depth spectrum, the advantage is we can note different, we can see the subspectra for the different kinds of carbons. We can separately see CH3 carbons, we can separately see CH2 carbons, and by this we can know the total number of carbons and the nature of the carbons, whether it is a CH, the signal is due to CH2 carbon or a CH carbon or a CH3, we can know it. So that is the meaning of the using the polarization transfer techniques.
Ma'am, only will use protons and carbons or any other one?
Normally, this is more studied with respect to proton and carbon. That's the reason I said it is restricted to proton and carbon. We can apply even to other different nucleus also.
Okay. So out of 1 and 2, which is the best, ma'am? Which one is the more powerful?
What 1 and 2? 1D and 2D. 2D is definitely more powerful, but we don't use it when. And suppose, for example, as I said, if you want to talk about the ethanol spectrum, do we use 2D NMR? Like I said, the most powerful technique is used, our most powerful weapon is used only when in the case of need. We don't use it as and when we like, isn't it? We are not going to play with it. Like for example, there is one saying in Telugu, "Pichiki meeda Brahmastram." Do we? Yes, Sama?
Yeah.
So for knowing the structure of ethanol, 1D NMR is sufficient.
Okay. Okay.
Only for complex molecules.
Ma'am, really it's wonderful, ma'am. Very innovative information to especially our pharma students. There is a lot of appreciation is coming in chat box. Really, ma'am, very thankful. Totally your talk. Yeah, we
The
learned.
participants, I think one thing, Prabhaker Reddy, the participants are only from national level. You have participants here now today for my session,
Yes,
or even
yes, ma'am.
only national level?
Yes, ma'am. Only national.
No international.
No.
Speakers
No.
are international and attendees are national.
Yeah, speakers are from international.
Speakers are from international.
Yes, yes, ma'am.
Okay.
Because the
Anyway,
timings are different, ma'am.
yeah, timings are different. That's the
Timings are
thing.
different.
Yeah.
Timings are different. Yeah, that's the main thing. They don't interact.
Yes, ma'am.
But anyways,
So really,
thank you.
ma'am,
Thank you for giving me the opportunity to share my knowledge with the participants in the international webinar. And I once again congratulate the organizers, especially Prabhaker Reddy. And as I know, Prabhaker Reddy is known for such things. He's the first of such kind to organize an international webinar. And I didn't know when I was actually asked for to deliver a lecture. I thought maybe it's just like that. But when the flyer, when I've seen the flyer, then I thought, oh, this is an international webinar. Then I thought, no, definitely I'm privileged to give a talk in the international webinar. But in the initially, I felt bad because I am given the last session. But finally, I thought, okay, let it be. There is a saying, but better late than never. So I thought, okay.
no, ma'am. Right
Anyway.
from beginning, full, ma'am. Your chat box is full. A lot of people are waiting outside, ma'am.
You could have
No
given them
space.
a link through YouTube, no?
Yes, ma'am. Yes, ma'am.
Mm.
A lot of response came from YouTube also, ma'am.
Yeah.
Really, we are very thankful to you. We, as your talk, we learned the following things, ma'am. Preparation, evaluation, mixing, detection, and experimental procedures, different techniques like 2D, ROSI, COSI, TOXI, and HMQC, HMBC, NOISI, 2D inadequate, and like peaks in HOMO and diagonal peaks, off diagonal, cross peaks, regular proton, 13 carbon, HECOR, DGPT, 2D inverse detection techniques. Really, ma'am, it is very, very useful, especially our inform analysis and pharmaceutical chemistry people.
Yeah, in pharmacy. Even for the teachers, those who are taking up this particular topic, it will be very useful for them.
Yes, ma'am. I saw all the feedback from, especially from Tamil Nadu, Madhya Pradesh. They given a lot of feedback, ma'am. Really, I'm very thankful to you. Wonderful session. Even though you say loss, but it is wonderful. No need to say that loss or first, ma'am. Every session is 100% successful, ma'am. We are getting a lot of feedback from all the viewers, total nation. Really, we are very wonderful and we are very happy. We are very thankful to our administration staff for providing this opportunity, ma'am. Once again, thank you, ma'am, for your valuable time.
Thank you, Prabhaker Reddy, and thank you all, especially the technical support given by Arjun.
Yeah, Arjun and Anjaneyulu, ma'am.
Anjaneyulu also.
Yes, ma'am.
And I'm seeing in Swati in the this thing.
Without their support, we cannot come at this.
Yeah, that's true. Yeah, and especially thanks Sarita for contacting me.
Of your talk, ma'am.
Yeah. Okay. Thank you, sir.
Thank you. Sarita, what to Sarita? What are thanks? Hello, Sarita, are you there?
Unmute, madam.
Yeah, it's already unmute, sir.
Yes, now you.
Thank you for a wonderful session, madam. A clear and concise explanation of 2D NMR technique. It's a very useful for our B.Pharm and M.Pharm students because they're having a common subject for all specialization in N.Pharm. And also thanks to Principal Sir for organizing this webinar series. And also thank to administrators. Also thank to everyone who are part of the session. And a special thanks to Arjun Sir and Anjaneyulu Sir. And cooperation of our team making the grand success of our webinar. Thank you very much, madam. You are giving a valuable time to our webinar series. Thank you very much, ma'am.
Thank you.
Yeah, thank you. Thank you, Sarita. Now we have other speaker is ready. Now I will invite Sushmita ma'am. Are you there, ma'am?
Sushmita.
Go to Sushmita.
Yes, sir.
Yeah.
Sir.
Please introduce our speaker.
Welcome to. Yes, sir. Welcome to Palamuru University, University College of Pharmaceutical Sciences, collaborated with Indian Pharmaceutical Association. So, International Webinar Series 2020, which is the last session, 12. And good morning, good evening, everyone. I am K. Sushmita, Assistant Professor, University College of Pharmaceutical Science, University. Firstly, I want to welcome Vice Chancellor, Palamuru University, Rahul Bojjagaru, IAS, and Registrar Palamuru, Dr. Pindi Pavan Garu, and OSD to Vice Chancellor, Dr. D. Madhusudan Reddy Garu, and Controller of Examiner, Dr. N. Kumaraswamy Garu, and Principal and Chairman of Webinar Series, Dr. V. Prabhaker Reddy and V. Prabhaker Reddy Garu. Thank you. Now, I welcome today's speaker, Dr. A. Kalyan Chakravarti Garu, who is Associate President of Dr. Reddy Laboratories Limited. So, he is going to share his valuable information on compassionate medication emergency utilization. So that I want to give just a brief introduction about Dr. A. Kalyan Chakravarti Garu. Sir had awarded his doctoral degree in synthetic organic chemistry from Kakatiya University. Sir had received his PG diploma in intellectual property management and also received his Bachelor of Law from Osmania University. Sir had 12 years of experience in pharmaceutical research and development. As a result, he contributed to synthetic organic chemistry in 3 major areas of research: was new chemical entities containing heteroatoms, polyethylene glycol chemistry, non-integral process soluting for API. Sir had experience in both academics and professional research, which in biological active molecules containing heteroatoms. Sir had worked on new chemical entities, biologically active analogs, and amino acid analogs. Sir had worked with a number of global MNC pharma companies. He had played different roles in organization. Sir had awarded different nominations, memberships, and special awards. And he had awarded a gold medal and cash prize sponsored by Osmania Graduate Association of Hyderabad for being ranked as the first in college BSc. He is a member of American Chemical Society and member board of studies in Department of Pharmaceutical Sciences, Acharya Nagarjuna University, Guntur. He is the referee for Indian Journal of Chemistry and Heterocyclic Communication. Sir also had awarded national and international research publication. He also guided PhD scholars from different cities, and he had traveled to different countries for attending the conferences. Thanking you. Now, I would like to start the scientific session by our speaker, Dr. Kalyan Chakravarti Garu. Welcome, sir.
Good evening. Am I clear to all of you?
Yes, sir.
Yes, sir.
Good evening, sir.
Good evening, Professor Prabhaker Reddy, and good evening, my dear pharmacy community friends from the Department of Pharmaceutical Sciences, University College of Pharmaceutical Sciences, Palamuru University, and the administrative heads, OSD, Registrar, Controller of Examinations, and the lady who has, spoke about my CV.
Sushmita, sir.
Sushmita, and thanks for thanks for all your introduction, and it gives me immense pleasure whenever I am connected with Prabhaker Reddy, Palamuru University. This is my third one in a series, and I wholeheartedly congratulate my dear buddy Prabhaker Reddy, who has been putting his best efforts in spite of this COVID-19 pandemic situation and the financial constraints which he has in handling these kind of issues. But whatever may be the case, every July he comes out with a poster, with a very colorful, very vibrant poster, and it was very heartening to see a lot of my old friends who are placed outside India, who are doing their best in academics and also in research. And Prabhaker Reddy could bring in everybody online as per the availability of their time slot. And he has been managing this webinar series for the past 7 days. And fortunately or unfortunately, I have been given the last slot of the series, but last is never the least. Okay. And it is a great privilege for me to associate with these budding young pharmacists and also the learned teachers And the lecture which is just completed by Professor Girija was really thought-provoking, and I went back to my master's days when she was talking about nuclear overhauser effect, COSY, NOSY, 2D NMR, and that was really wonderful. And I would kind of recommend Prabhaker Reddy to have all this information posted on the UCPS website in the name of web series, and whoever is interested to learn the topic, they can definitely refer, because most of this information is available on Google, but at different places. She has made it a very palatable format, and which is very much necessary for a person who is in chemistry or who is in pharmaceutical industry to understand the analytical technique of NMR, structural sedation. And this is one of my recommendation before I start my topic. And today I would like to take you through few very dry topics. Though it is dry, it is the need of the hour. Why it is need of the hour is everybody knows that we are experiencing the very much unknown friend called as coronavirus. Nobody knows its behavior. Nobody knows its proper structure. We have only identified certain strain, and we are trying to fight with that strain with some known candidates, known drug candidates, and unknown drug candidates. So in the process, there is a role of Ministry of Health or US FDA or Food and Drug Administration, which is called as regulatory agency of the respective country. In India, it is CDSCO, Central Drug Standard Control Organization. And in US, it is US FDA. In Europe, it is EMEA. In South Africa, it is MCC. In Australia, it is TGV. So like that, every country has their regulatory body which governs the laws of a product to be approved, to be banned, and to be permitted under emergency use. So I would like to take upon what is emergency use authorization or compassionate medication, and how does this benefit in pandemic situation or in emergency conditions. So it would be a simple 21 slide deck, and I will keep running them. And whenever somebody has any doubt, please post on the chat box, and I will be more than happy to answer any kind of question in the process. And if you allow me, Prabhaker, I will just share my screen with the presentation.
You can share, sir.
You can share, sir, please. You can share, sir.
Can you see this?
Yeah.
Visible, sir.
Thank you. So the title of my talk would be Emergency Use Authorization, which is also called as compassionate medication. I would only touch base how does the law regulate, and couple of cases, a couple of case studies which helped the citizens of the planet to get access to this kind of medication. And the data presented here has no relevance to Dr. Reddy's. This is purely collated by me, and any responsibility lies upon me only. So what is emergency use authorization? It is also called as expanded access, pre-approval access, special access, compassionate medication, emergency treatment. All these are interchangeable terms which refer to the usage of the drugs. While the compassionate medication or compassionate drug use is usually a colloquial sense for individual requests, expanded access official term which is designated by US FDA. And as a body where US FDA defines the compassionate medication, it states that expanded access is the usage of an investigational drug when the primary purpose is to monitor or treat the patients. So just to give a more comprehensive thought on this, the compassionate medication allows the investigational drugs which are not approved, which are under clinical research, which are under clinical trials, to the patient who is in need. Basically, if you don't have a therapy, or if you don't have a disease treating capability of a drug which is available in the market, the investigational drugs under special circumstances are allowed to be used by the patient under the doctor's supervision, under the supervision of a medical practitioner. And this is emergency use authorization general terminology. And how does US FDA define? So an emergency use authorization in United States is an authority granted by the US FDA under sections of Federal Food and Drug Cosmetic Act, which is a part of 2013 PAH PRA, and this does not constitute approval of the drug in full form. The meaning of this is it is only allowed to be prescribed to a pool of patients or a set of patients when there is a state of emergency, when there is no alternate therapy, when there is no suitable drug candidate for the treatment of unknown disease or a material threat. Under these circumstances, US FDA has formulated this guideline. And the current scenario, whenever we talk about the products which are under treatment used for the treatment of coronavirus or COVID-19, the majority of the news items which cover remdesivir, favipiravir, all these products are allowed under emergency use authorization because of the state of emergency, because of the non-availability of therapeutic candidates to treat this pandemic situation. And even the WHO also gives more or less the same kind of definition for compassionate use, the program that is intended to provide potentially to the patient suffering from some kind of disease which has no satisfactory medication. And more or less, the Indian scenario also, extracts the similar kind of terminology, bibliography, definitions from US FDA and WHO terminology. The Central Drug Standard Control Organization, which is the regulatory body of India, as per the Drugs and Cosmetics Act 1940 and Rules 1945, which are amended as of 31st December 2016, the CU allows access to the unknown medication or the medication under investigation to the patient where there is no alternate therapy. And even the rules 33A, 34A of the DNC Act 1940 and rules import allows us to import small quantities of new drugs which are not approved in India. So this is something over and above the usage in India. If it is not available, if it is not marketed in the country, then you are allowed to import in small quantities for your personal use under special approval from SEDESCO. And just to give you some examples, we have gone through certain hard times in 1940s, about tuberculosis, where the compassionate use of bedaquiline for multi-drug resistant tuberculosis was not accessible. Then the government has come into the picture and they have, allowed this particular drug. And how does the compassionate use programs work? I've just done a simple mathematics just to give you more understanding on how does the term compassionate use works. So the importance of free access of these drugs through CU program cannot be understood. This can be, evaluated by the fact that a course of bedaquiline and delaminate would cost a patient in India around 18 lakhs to 25 lakhs respectively through international importation. And because these drugs are under patent protection, these were not allowed. So once the CU program has been approved by the government of India, these drugs were accessible to most of the needy patients at a very, very cheaper and affordable price. This is one typical example which everybody have gone through this from the past 45 to 50 years for multi-drug resistant tuberculosis. Now we are getting into a case study. This talks about a product which is called as favipiravir. this is a drug which was originally indicated for some kind of influenza strains. This is approved only in Japan in 2009. And the use of favipiravir for coronavirus has been evaluated in the last 4.5 to 5 months. I will just take you what made on favipiravir, how is that being included in the compassionate medication or in the emergency use authorization. So favipiravir is a simple heterocycle molecule which is approved for a label indication with the nature of antiviral medication to treat influenza in Japan. And currently it is being studied to treat a number of other viral infections like the experimental antiviral drugs. All these are innovator products, invented by Fujifilm of Japan. And the mechanism of action is provided here on the right hand side. And from February 2020, favipiravir is evaluated for the use in the patients who are suffering from mild to moderate coronavirus COVID-19. And there are about 19 clinical trials being which are under progress across all these countries: Japan, Italy, Kuwait, Brazil, Stanford University, and Russia. Yesterday they have made a press note that favipiravir is providing a promising activity and it would be approved by Russian authority also. This is the basic information about the product. And the favipiravir compassionate use in Japan, there was a clinical trial conducted on 2050 patients with an administration which is now under progress for a period of 7 to 14 days. For, as I told you, it is on the mild to moderate patients. And this product is approved in India, Italy, and China for experimental use or compassionate use in COVID-19 patients only. And there is an array of clinical publications which are happening, which in the recent 3 to 4 months, you could see maybe around more than a dozen publications which were published by very reputed journals, which talk about the efficacy and safety of favipiravir when administered to mild to moderate patients undergoing coronavirus disease. And the dosage regime, the strength, the dosage is very well published in most of the journals. And how does favipiravir as a broad spectrum antiviral act? Just wanted to give you the historical information. In 2011, how does Japanese PMDA application, how does PMDA review the application for seasonal influenza A and B virus infection? And this was approved in 2014. Sorry, I told you as 2009. It is 2014. And this is a 6-year-old drug whose label expansion is now under progress. And the multi-use and use for different indication is now being evaluated. So the position of favipiravir in the treatment of coronavirus, you could just go through the points. Only medicine approved in some countries for the treatment of mild to moderate cases. And there is a endpoint observation, mild to moderate cases, where 80 to 90% patients were achieving the endpoint for all the COVID-19 cases. And it reduces the burden on healthcare system by preventing slippage of mild to moderate cases. And the viral load reduces in the patient within 4 days. The first 4 days, the viral load continues to be fragmented, but once the dosage has been inhibited, and the viral load has been significantly observed to be coming down, it is a oral drug which is easy, and there is no compliance problems, and prevents further risk to community by patients needing to visit hospital, reduced burden on healthcare. And this is the clinical research across the globe. This was obtained from the clinic options. And on favipiravir, starting from January to March, and the blue color talks about the number of clinical trials happening in USA. And the remaining, so if you could significantly watch this slide, you could observe that huge number of clinical trials are being undertaken in US. And this is one observational study. So this is the observational study which is happening in Japan with about 2,100 patients. And the objective of this study is to observe the virus load reductions by in the mild to moderate patients. I would like to share you, just a second. Prabhaker, can you see me my another share?
Yes, yes, yes.
Yeah, so this is a US FDA website where the clinical trials which are now ongoing. I have captured this information till 13th July, till yesterday, on favipiravir. There are about 16 trials going on. Favipiravir therapy in adults with mild COVID-19, and the status of recruitment of the patients, and if there is any study result after after the evaluation and testing, the results will be updated on a daily basis. This is a official US FDA's website information, clinicaltrials.gov, and I just wanted to show you how the pharmaceutical companies and universities are currently working to address this major problem. One single drug which is approved in 2014 and now being evaluated by so many companies in so many countries for the same problem. This is the first time something so dynamic is happening. And if anyone has patience and some kind of interest, if you open this website clinicaltrials.gov, there are about 2,900 studies going on for coronavirus with known drugs which are already approved in the history, starting from hydroxychloroquine sulfate, betamethasone, dexamethasone, favipiravir, and lopinavir, ritonavir. All these products which are used for some other indication are now being evaluated in the treatment of coronavirus or COVID-19. So just imagine somebody spending so much of time, so much of efforts, so much of money for this problem using a old drug candidate. This is really heartening to know, and I want all the students who are now pursuing whether their master's program or bachelor's program just to spend some time in the clinical research area, because every individual has some different level of intelligence and their knowledge in assessing the requirements, in addressing the current need. If you can just look at the structure of favipiravir and identify a diazide compound which has similar nature, which has antiretroviral or antiviral activity, can definitely suggest this kind of inputs to any big global pharma company with a simple molecular modeling technique. That will definitely give you a lot of satisfaction. That will also help the people who are suffering with this problem. So as a result of the ongoing studies, what is the outcome for this particular product? Data from clinical studies suggest faster viral clearance, faster fever resolution, faster resolution of chest CT changes, faster clinical recovery. So based on these 16-17 clinical studies which are ongoing, the first set of studies which were completed with between 7 to 14 days, this is the study outcome, and there the observations and inferences suggest that favipiravir as a product has a comparative viral clearance, comparative better viral clearance, faster fever resolution, because this is only administered for the mild to moderate patients, and generally clinical study happens in multi-centers, and if it is a global clinical trial, it happens covering almost all the 7 continents people. And since this is a pandemic indication, the studies are focused in the respective countries only, and simultaneously these studies are clinical research is being done in almost all the countries. Today I was only able to cover the clinical research happening in US because of the time, and the information very much available in the public domain. The clinical studies which are going in India, I couldn't get that information because it was not updated. So I would rather try to collate that information and send it to Prabhaker so that it can be shared to the students and the other community people. And the inference of this clinical research is high rate of viral replication can be controlled with early use of favipiravir. If the virus is identified or diagnosed in the initial days or initial hours, administering favipiravir is going to be definitely a boon and a help. So that is the outcome based on these 16 clinical trial studies, which some of them are ongoing, some of them have completed, some of them are yet to take off. And the second case study which I wanted to touch base is remdesivir, which is an investigational new drug in US and also in majority of countries. This is absolutely a new product which was not known to the mankind. This was under clinical trial phase 1. And the moment there was some news on this product, your principal asked me what is the background and how does this work. And I have shared him the US FDA's comments on 1st of May 2020 because this product was allowed to Gilead Life Sciences in US to be used for the COVID-19 patients at a severe stage COVID-19 patients. And this is again an emergency use authorization. This is not a clean approval. This is only an emergency use authorization. We just go through this product also. This is a complex chemical structure when you compare with the favipiravir. This has about 4 chiral centers, and the chemistry is also pretty complex. It involves 33 chemical stages, chemical transformations. The total synthesis of this product took 14 months for the innovator after establishing the R&D trials. And now the innovator has signed a deal with 5-6 companies across the globe for supply and distribution of this product. This particular medicine is available in US at $3,400. In India, this product is sold, I think, at probably at 6,000 rupees per vial. Hetero is marketing this product in India, and even companies like Dr. Reddy's, Cipla, would enter into the market after the regulatory approval. This is indicated for the treatment of suspected or laboratory confirmed COVID-19 in adults and children hospitalized with severe disease. The first product which we have seen is mild to moderate. This is administered for severe disease, and the indication also, if you could see, suspected or laboratory confirmed. So there is no clear evidence on usage of this product. It is only a investigational usage which is now allowed. So the global status of this product, remdesivir, which is called as Gilead's 5734. Europe, it is approved in April under emergency use authorization, and US FDA May 1, 2020, and even in Japan, it is allowed on May 7th, And in India, it was allowed access has been allowed on 1st of June 2020, and few more countries are being added. France and Italy will be added by this week. They are at the verge of approval, and more or less the indication would be the verbatim would be different, but the content of the indication would be almost same. And this is how Remdesivir Act, it is a graphical representation of this product. How does this act as a ACE2 receptor? And I do not have much knowledge on this one. This was prepared by my medical affairs colleague. She is a MD pharmacology, and she helped me in creating this particular slide. And Remdesivir known to be it interfaces with the action of viral RNA dependent RNA polymerase, resulting in delayed chain termination during replication of the viral RNA. So this will not allow the replication of viral induced RNA. This only delays. As a result, you could see the virus infection or the viral infection disappearance. And the dosage and administration of this product, for the treatment of suspected or laboratory confirmed COVID-19, which I just told you. And severe disease is defined as patients with an oxygen saturation of less than or equal to 94%. So now you could see in many research publications or many social media that the oxygen levels, the saturation level of oxygen is being monitored in majority of hospitals and also in the apartments. And if the saturation is found to be 94%, it indicates that there is a severity in the virus infection. That is one kind of indication. And the dosage here is a single loading dose of Remdesivir 200 milligram on day 1, followed by once daily maintenance for about 9 days. Totally, 2 grams of the product would be required for a single patient to get rid of this viral infection. And in adults not requiring invasive mechanical ventilation or an ECMO, a single dose of Remdesivir 200 mg day 1, followed by once daily maintenance of 100 mg for 4 days. So if you could see in a patient who is not on ventilator, the dosage is different, and the patient who is on a ventilator support, the dosage is different. And this is the summary of clinical trials which are ongoing or which are completed in various countries for Remdesivir. The first trial happened is in USA for about 1,000 patients. The second trial, safety and antiviral activity of Remdesivir in participants with severe COVID-19. The patient head count was 397. And the third trial was safety and antiviral activity of Remdesivir in participants with moderate COVID-19. So the safety of this product has been established very well. The efficacy is still under evaluation since it is an investigational new drug in US and in other countries. The efficacy is now under trials, and we might get some kind of inference in next 2.5 to 3 months on the efficacy part of this product. And since safety is very well established, the medical doctors are not very much worried, because it would be a trial and error kind of treatment using Remdesivir. And if you talk about the efficacy, and this is the summary of efficacy, we have gone through the list of clinical trials where there were a couple of studies, one study, 1,600 patients, that has been published from Remdesivir clinical studies. And it had a faster time to recovery than placebo in adults hospitalized, and evidence of lower respiratory tract, whatever we just gone through in both the scenarios, with ventilator, without ventilator, and the dosage regimen is different. The odds of improvement in the ordinal scale score were higher in Remdesivir when compared to the placebo. Of course, that is natural. And in the cohort of patients hospitalized for severe COVID-19 who were treated with compassionate Remdesivir, clinical improvement was observed in 68% of patients, and all these are under investigations. There is no clear evident data which can confirm that this product is efficacious. It is only a trial and error which is happening now, and maybe by end of September we would see majority of the trials get closed, depending upon the registration of the patients, depending upon the achievement of the end point of the clinical trial protocol. And this is about the safety. This also talks about the this also talks about the serious adverse events when were reported of 114 of basically 21% of the total population which underwent this clinical study had some kind of adverse events. And when the adverse events are graded between 1, 2, 3, 4, grade 3 or 4 adverse events occurred in 156 patients, it is higher than the normal grade 28.8 in the remdesivir group. So no new safety signals were detected in the recently published compassionate use cohort study. This is the summary of the safety of remdesivir, and why I have picked up these two products is the first one, which is favipiravir, whose safety and efficacy has been well established for influenza virus A and B, and the safety in spite of drug loading up to 30 to 35 grams of the favipiravir product, it is found to be pretty safe, and the accessibility of the drug is very much easy to the people, and the compliance part, it has no side effects at all. And that has been showing promising activity in the mild to moderate patients, and remdesivir found to be acting comparatively better than placebo since it is under investigation, and this is only available medication for severe virus infection COVID-19 patients. So these two products, which are now available in India for Indian population, because we are all in the healthcare segment, I wanted all of us to understand the clinical research underwent before these two products hitting the market or touching the patients, and you will be able to help or guide your neighbors or your friends or relatives and colleagues to kind of suggest them and to evaluate whether they are being given the right treatment in the hospitals, whether government or private, and you would be in a better shape to judge whether your near and dear ones are under safe within the safe hands of any hospital. So that was my motivation to pick up something which is different and something which is not so relevant to academics. I just wanted to be cognizant to give you very relevant information, packed in these 24-25 slides, so that it will be easily understandable and it would be palatable for all of you. And this ends my topic today, and I would be glad to answer or address any questions pertaining to this one. And I have few, one. So I have something, which I always do at the end of my session. I wanted my young friends who are now pursuing their bachelor's and master's course to just go through all this. Everybody knows we know them, and I wanted you to just read through these 7 commandments, so that whenever it is relevant to you, please apply that. Continuous learning and knowledge enhancement. Without that, you are nowhere in the market, and you should always be sharp, looking out for the better opportunities. Now everybody in the world, they started using their own old products for the new indication. So it is very easy. So basically it is as good as pulling out your Hero Honda 1996 model and then updating it and taking onto the roads. Without hard work, nothing grows but only weeds. The most certain way to succeed is always try just one more time. And it always seems to be impossible until it is done. The key differentiator is moving from 0 to 1. And the moment you get onto 1, the numbers are only numbers. You should only you should only continue your walk. And the last one is, learning is like God. It is available everywhere in the form of Prabhaker, in the form of your other professors and teachers. Just oblige them, just listen to them, and refer documents, do not refer notes, only refer the textbooks and reference books. That will give you a broad perspective. Thank you, Prabhaker. Thank you, the Department of Pharmaceutical Sciences, UCPS, Palamuru University, for extending your invitation to share my thoughts. And I know this is not a relevant topic, but I thought this is relevant for today, not for your academics, whether it is B.Pharm or M.Pharm. It is relevant to every individual. It is relevant to today. That was the reason I had to pick up this topic. And definitely, I will look forward for another chance, wherein I will touch upon your a topic which is relevant to your syllabus book. Thank you, Prabhaker.
Yeah, please stop share. Can you stop your sharing?
I will do that one.
And there are a lot of questions on chat box.
Yeah, I'm just opening the chat box.
Please, please.
Can somebody read it for me one by one?
Yeah.
Sir.
Sushmita, can you read?
Sir. Sir, among the currently used medications for COVID-19, which medicine has been proven as promising one for it?
So there is nothing which is proven. It is all these medicines are under investigation. So it is our assumption, it is our knowledge that favipiravir and remdesivir are known to be better options.
Okay, sir. And next question is, sir, can you explain about repurposing of drugs for COVID-19?
Can you please pardon me?
Can you explain about repurposing of drugs for COVID-19?
Yeah, repurposing of the drug is known drug for an unknown indication. It is just repurposing of a drug. So favipiravir is a best example, which was originally indicated for influenza A and B in 2014, is now being repurposed for COVID-19. This is one of such kind of drug. And there is a huge array of drugs like lopinavir, ritonavir, hydroxychloroquine sulfate, which is used to treat malaria, is now being used for the being used as the first line of defense for COVID-19. So I can send you about 14 to 15 drug list which are being repurposed.
Next question is best clinical efficacy.
Clinical efficacy is still under evaluation. Safety has been established for remdesivir and also for favipiravir. Efficacy is under study now, madam.
Okay, next question is Dr. Reddy's labs coming with any drug or vaccine for COVID-19?
Yes, we are coming with both favipiravir and remdesivir. In next for 30 days, you will see our brands in Indian market.
Next question, sir. COVID-19 drugs are very costly enough through. They are old antiviral drugs. Can you justify?
No, they are not costly. Basically, if you wait for another 30 days, you will see 4 or 5. Even today morning, if you look at the CDSO website, they are evaluating the approval of BDR, Cipla, Sun Pharma for these 2 products. By tomorrow, this time, you will see 3 more products coming into India market. As a result, the competition will be less and the price will come down.
So next question. Every day corona changing its shape, then how the antivirals will work? It's going on mutations.
So basically, we have to boost our body with a lot of immunity sources. The best medication is, 3 things. Sleep for 8 hours, have nutritious food, away from tensions and stress. If you are these 3 things, I don't think virus will touch you. Basically, if you are clean and clear, if you have enough immunity in your body, if you are away from stress, if you take 8 hours of sleep time, I think that would be the best. And of course, keep away, stay safe, stay at home. That's all.
Sir, next question, sir. Do remdesivir is working or show its effect on severe cases, and what are its side effects?
So side effects, we have seen there are serious adverse events in 28% of patients. And I can send you the clinical trial summary along with my presentation. There is a complete detail of the serious adverse events in each of these studies.
Sir, then 2 companies came as oral and parenteral. And what about Dr. Reddy's?
We are coming oral and parenteral. Remdesivir, we are coming parenteral. Favipiravir, we are coming oral.
Okay, next question, sir. Can you explain about Covaxin? What are the outcome results expect based on your research knowledge?
So Covaxin is a investigational drug, which is a vaccine being developed by Bharat Biotech. And last month, Indian Council of Medical Research has allowed this vaccine to be tested for Indian population. They have registered this clinical study, and 60 patients. The study is now going on 60 patients as an investigational new study, and the first line of inference is expected by 6th of August. And until then, it is completely, it is a trade secret, and nobody knows how the study is progressing. And even the clinical trial website of India doesn't feature the study. That's the reason I could not provide that information in my presentation today.
Okay. Thank you, sir, for answering the questions with patience. Okay, you have given a lot of information about COVID-19 and what are the treatment, what are the drugs that are coming. Now over to principal, sir. He'll give a brief discussion about talk.
Dr. Kalyan, really it is a wonderful session. We are very happy because I think you got more questions compared to all 13 speakers. So people know that you are going to give the answer because you are the live person who is working in industry since 20 years. So I just wrote down very important points what you talk about. Even the title is a little bit tough to understand, especially our budding pharmacists. Emergency use authorization, compassionate medication. Really, it's very, very useful, and you given answers about repurposing of drugs and about remdesivir, flavipivir, and old drugs with new indications. But my question is, even today I'm saying, like previous Sushmita is asking, changing the shape, no. So how these drugs are useful? There's a big worry. Can you add some more information?
Thank you, Prabhaker. The nature of the virus, all the research scientists could identify one strain of corona for which the treatments are now undergoing. And as the strain is progressing, basically, the physical parameters and the body structure and body chemistry are the three important elements which allows or which doesn't allow the nature of the strain to change. So that would be studied while the clinical research is now going on. So there are about 2,900 studies, as I told you in my first opening comment, and each of the study has a different objective. Few studies are, undertaken just to see the efficacy or the toxicology or the safety of a particular drug. But there are about 650 studies which are studying the nature of the strain, how the strain is changing its physical and chemical structure. So that is yet to be answered, and even I don't have an answer for that.
Yeah, regarding vaccines also, how many days are required for minimum in animal studies?
So preclinical and clinical, as per Schedule Y DNC Act in India, the preclinical study generally it happens within 4 months, and clinical study phase 1, phase 2, phase 3. Phase 1 between 60 to 80 patients. Phase 1 establishes safety. Phase 2 efficacy between 200 to 400 patients. Phase 3 between 600 to 1,200 patients. This is as per Schedule Y. But since this is a compassionate use and emergency use authorization, I don't think that systematic clinical trial rule is applicable. Bharat Biotech has come up with only single study on 60 patients, of which 39 patients were registered, and it is now going on. I think they will get a conditional approval after the completion, after reaching the end point. Probably they will be asked to do a post-marketing, or they would be asked to continue their study. However, in the meanwhile, the accessibility of Covaxin will be allowed to the patients in India.
Yeah, so people have a different opinion that less time, then how the drug will act on the patients. It's a big question.
No. Basically, one is better than zero.
Okay, Dr. Kalyan, really is a wonderful session. And this is a last talk out of 14 speakers. You are the last one. And your last slide, ticket to win 7 components. Really, they are very, very important for our young budding pharmacists. And every year you are giving a lot of knowledge to our students. And this time, no, I planned this webinar because of Corona, but there is a lot of rush in Zoom as well as YouTube link. Really, I'm thankful to all the audience, especially students, teachers, and the patient listening since 2 o'clock. And within 5 minutes, we are going to start our validation session.
I have one comment, Professor.
Please.
So, Corona could stop anybody, but not Prabhaker Reddy. So, I was trying to comment that coronavirus could stop the world, but not Prabhaker Reddy. He did not stop conducting the symposium, and he has changed the format from a face-to-face to virtual format. But everything in the world stopped except Prabhaker Reddy. You are muted.
Muted.
You are muted, Prabhaker.
Yeah. Dr. Aliya, thank you, because now students are eagerly waiting for seminars. So that is the reason during this Corona pandemic season, we started this, and we are very much thankful to our Vice Chancellor, Rahul Bojagara, AS, and our Registrar, Professor Pin Pawan Kumar, and our OSD2 Vice Chancellor, Dr. Masudan Reddy, and all technical staff, especially Dr. Arjun and Dr. Anjaneyu. Without their help, we cannot do all these things.
Very Silesh. I could not see Silesh today.
Yeah, this guy is not there. So, Kalyan, can you call our...
Yeah, I'll call.
Yeah, please.
I am signing off now.
Yeah, please. No, Kalyan, you should be there.
Okay, okay.
Yeah, please call our chief guest now, because he's not lifting my phone.
Okay.
Then we will close within 5 to 10 minutes. Shubha, can you give vote of thanks for sir? Then we'll start the valedictory function. So, Shubha, are you there? Hello?
Thank you, sir. Thank you for your valuable information on corona and what are the drugs we have to take, and what are the clinical trials are going in worldwide, and what are the drugs, antiviral drugs, which we have already performed drugs. And now it's time to end the session. And I want to thankful to the University College of Pharmaceutical Sciences, Dr. Prabhaker Reddy, sir, because he from the first day he is keeping his patience and giving the sessions completely. And now I want to thank to the administrators from the technical team and behind the webinar, Dr. Anjaneyu sir and Arjun sir, and to all my colleagues who supported me in all aspects. And thank you for the Zoom participants and YouTube participants. Thank you, sir. Thank you very much.
Thank you, Sushmita. Now I request our OSD2 Vice Chancellor. Sir, are you there, sir? Madhu, sir. Arjun, sir.
Hello.
Yeah, sir, please, sir.
Yes, sir.
Yeah, just now we completed Kalyan talk, sir. Now we are going to start panelic session. So I need your blessing, sir.
Thank you, sir. Yeah, good evening, everyone. It's really a most memorable moment for our university and even for the Department of Pharmaceutical Sciences. So it has been a really hectic schedule for Dr. Prabhaker Reddy, sir, and his team. As you know, almost from 8 days, they are struggling, and almost 14 sessions have been done. And it started with very good lectures and ended with a bang with Professor Girija ma'am and even our university well-wisher Kalyan Garu, Dr. Kalyan from Reddy Laboratory. Really, I thank all the resource persons who have given their valuable time, and because such tough times where we are facing, like COVID-19. Especially for academics, we were never used to such platform, but such challenges will make us very strong, and especially for Palamuru University, which is located in a rural area where we had tough time with net connectivity and because of bad weather. Still, the Department of Pharmaceutical Sciences, they have conducted this webinar successfully. So I congratulate the principal, Dr. Prabhaker Reddy, and his committed team. And really, it's a very good event for our university. And in future, we'll try to rectify whatever mistake we had done, maybe because of technical glitches actually. So that we will try to overcome. And next time we will have a most decent and better international webinars. And really, I congratulate Dr. Prabhaker Reddy. Thank you, Ananda. Thank you.
Thank you, Master. Thank you. Thank you very much for your valuable time. Even though you are in with IAS office, even though you given brief information and blessings us, definitely, sir, we'll do a lot of webinars in coming days. Now I request Dr. Kalyan Chakravarti Akula, please give your message to our budding pharmacists.
At the outset,
You are my chief guest.
so can you hear me?
Yeah, please.
At the outset, I would like to congratulate wholeheartedly the team behind organizing this very interesting series of web seminars. Starting from Sri Rahul Bojja, Professor Pavan Kumar, Dr. D. Madhusudan, Dr. N. Kumaraswamy, Dr. P. Sujata, Dr. Chinna Devi, Ravi Kant, Tarun, Sailesh, Suresh, Isha Kumar, Someshwar, Sujata, Sharada, Swati, Susmita, and Sarita, under the captaincy of Professor Prabhaker Reddy, who has been putting unstinted efforts in ensuring, having all the most interesting topics on the board, and then getting people, talking to them, and having people like the IPC chairman, having people from Abu Dhabi, people from US, Malaysia. It was very, very heartening to see a government sector working like a private sector. Having a virtual conference in a government university with, I don't know the facilities. So he could install a lot of things in the last 3 years. But this webinar series, looking at the participation, 650 to 700 people, so many questions, so much of nice conversation, interaction. It has been a splendid experience for me. I never felt that I am talking to somebody in Palamuru University. It is as good as a pharmaceutical company or a corporate structured company lo unnatugane I felt. And thank you, Prabhaker. And I know wherever you are, you will absolutely excel, and you will always strive for a qualitative support to the students and your juniors. And I wanted each and every person who are a part of this program, on screen, off screen, students and the faculty, just take a cue from Prabhaker, and wherever you are, you continue to extend your support in the form of imparting knowledge, imparting some message to the young society, to the young budding pharmacists. That is the best thing you can give back to the society. So basically, you are the people who are building the society, who are, we are working and we are running our companies with the pharmacist, with the chemist, who are trained under you. So to give you in a better perspective, మీరు తయారు చేసిన మాలాంటి వాళ్ళు ఇప్పుడు కంపెనీస్ కి వచ్చి పర్ఫార్మ్ చేసి ఎక్సెల్ అవుతున్నారు. సో దిస్ ఈస్ నథింగ్ వాట్ వీఆర్ డూయింగ్. దిస్ ఈజ్ ఆల్ బికాస్ వాట్ ఐ హ్యావ్ లెర్న్డ్ ఇన్ కాకతీయ యూనివర్సిటీ, what I have learnt in my school, my college. And you are among those small cloud of people who are manufacturing excellent resources to the country, to the world. And I congratulate you, Prabhaker, and your very strong team of teaching faculty, and look forward for many more such kind of events. Thank you and all the best.
Thank you, Dr. Kalyan. Right from beginning, you are helping a lot. Even your company sponsored a big seminar, and every year you are coming and giving seminars to my budding pharmacists. Really, we will not forget. Even during Madhu's talk, he said well-wisher of Dr. Kalyan. So that is a image you. So really, because you love government colleges, because anytime I'm calling you, right from Hyderabad, you are coming on your own vehicle and you are delivering lecture. Really, I'm very happy, and our students are very happy. My staff is very happy. Even previous vice chancellors are very happy. So please continue your support in coming days. And we want to do many more webinars, especially for our students, because they are so much showing interest, because they are eager to learn what happening in the industry. Because nowadays, some people are showing more interest on industry people, and I'm calling academic people, but students' psychology is towards industry. Because unfortunately, our syllabus is different and industry concept is different. So we need some guidance, like you see, senior people, because you are since 20 years you are working in Dr. Reddy's. So your training is different, because our training is different. Even though we are making our students to up to the knowledge to the higher companies, MNCs like you. So coming days we will do more seminars. Really, I'm very thankful to my technical team, especially Dr. Arjun and Dr. MSR Anjaneyulu. Continuous support, unconditional support. Without that, we cannot do this effort. And especially my staff, right from everyone, I can name each and every person, non-teaching staff and administration staff, everybody. I'm very, very thankful to everyone, and especially present media, because they are covering every day about our webinars. Once again, Dr. Kalyan, please, you are, even though you have a meeting, I can understood, because in the morning I kept you because of your busy schedule. You even shifted to evening. Again, you have a meeting is going on, I know. So really, I'm very much thankful to you, because your commitment towards my university. And please, same assurance I need in coming days. And thank you one and all. Thank you, Kalyan. It's over to Arjun. Arjun is there?
Sir, I think Arjun is not there.
Not there? Anjaneyulu.
Okay, sir.
Yeah. Thank you, Anjaneyulu, for your patience, because since 1 o'clock you are sitting in internet.
No problem.
Really, I'm very happy, because of you today we are giving Zoom platform to all over the world.
Thank you very much, sir.
Kalyan, thank you.
Yeah. Bye bye. Thank you.
Arjun bhai.
Sir.
Yeah, can you close our event with your
Yes,
vote of thanks? So, go to Arjun.
1 second, I will take, sir.
Arjun,
He is there, sir.
your video is not showing.
Sir, 1 second, sir.
Please. So Arjun is our backbone. Anjaneyulu is our backbone. Because of these two guys, today I conducted these international webinars. So I need your support in coming days. Next month I'm going to plan UK seminars. So without your cooperation, I may not complete this. So please, all the participants, please collect your certificates. Google will give only 100 per day. So don't be panic. Next day you can try. Next day you can try. So our links will be open one more week. So once again, I'm thankful to all Zoom platform audience and YouTube audience. Your patient listening is very, very important for us, and your seriousness gave us to conduct some more webinars in coming days. Arjun, please.
Sir.
Yeah, now vote of thanks by Arjun.
Good evening, everyone. I take privilege to propose vote of thanks for this session. Really, sir has explained all the things which are relevant to the today's generation students, especially for the B Pharmacy and M Pharmacy students. Really, coming down online, in spite of busy schedule, sir has taken a good session, and in the post session, madam also taken a excellent session. So this series of webinars have empowered not only the students, but the teaching community also. So the overwhelming response has made us so enlightened that we have gone for the YouTube links too. People are waiting in the waiting rooms. For them, we have given YouTube live. For that reason, behind this is the dynamic principal, sir, who is behind this international webinars, and the administrative persons or the authorities who are behind this conducting the most relevant at this situation. I would like to thank our dynamic principal, sir, for his enthusiastic support throughout this series. Not only one webinar, I think today is the 13th or 14th one, I suppose.
Yes, please.
And with the enthusiasm, sir has started this, and today is seeing the wonderful success of this. A special thanks to the organizing committee and the conveners who has made a strenuous effort on doing this unflinching support, coordination, and the university authorities have that permission to connect the world with wonderful webinar session series. With these warm words and kind approach, every day we have been seeing now and then webinar in the morning and afternoon was excellent and informative. So I thank today's first speaker, Professor Girija Mangatar ma'am, and the next speaker, sir. They were in their seminar. Technology can't replace the great teachers, but technology in the hands of great teachers is transformation. These are the words I am not saying, but it is in the chat box. Now only I saw it. Thank you very much, sir, for this enlightening and astounding speech. Thank you very much for giving this opportunity. Thank you, one and all.
Yeah, thank you, Arjun, your valuable feedback. And I'm very much thankful to our beloved Vice Chancellor, Rahul Vajja IAS, and my beloved Registrar, Professor Pindi Pawan Kumar, and my close associate, Dr. Masudan Reddy, and all my teaching staff, nodding staff, and especially my special thanks to speakers, because they are very, very important. Without their knowledge sharing, today we cannot success like this. So really, I'm thankful to present media and everyone from right to my heart to bottom. I'm praying God, and coming days definitely will do more webinars for young budding pharmacists. And thank you very much. My special thanks to Dr. Arjun and Dr. Anjaneyulu. Thank you. Thank you, and all. Stay safe, be safe, stay healthy. Bye bye.